There is something watching you right now, not with eyes, but with presence. Ancient wanderers, older than memory itself, spinning silently in the darkness above. They have been there every night of your life, patient and eternal, waiting. What do they know that we have forgotten? When you were born, they were already ancient. When the pyramids rose from Egyptian sands, they were there. When dinosaurs walked the earth, they watched from above. When the first single-celled organisms emerged in primordial oceans, these travelers were already billions of years old, following their paths through the void. Every human story, every civilization that rose and fell, every triumph and tragedy played out beneath their silent gaze. But here is what nobody tells you. These are not just lights in the sky. They are worlds, 8 massive spheres of rock, gas, ice, and storm, each one carrying secrets written in the language of physics and time. Mercury burns and freezes in the same breath. Venus hides a nightmare beneath clouds of acid. Mars remembers oceans that vanished billions of years ago. Jupiter storms with winds that have raged since before humans existed. Saturn wears a crown of ice that should not still exist. Uranus spins on its side from an ancient collision so violent it changed the direction of time itself. Neptune races with supersonic winds in darkness, so complete that the sun becomes just another star. Why do they exist at all? What invisible force holds them in their endless dance around the sun? Ancient people looked up and saw gods. They called them wanderers because these lights moved differently than the fixed stars. The Greeks called them planets, meaning travelers. They built temples, tracked movements, created astrology and mythology around them. Were they wrong? Or did they sense something true that science would later confirm? Tonight we are going to uncover what the planets have been hiding. Each world holds secrets that will change how you see the night sky, facts that feel like whispers from the void, like messages encoded in orbital mechanics and atmospheric chemistry, 100 truths that sound like poetry but are written in mathematics. But the deepest secret waits at the end, something about these worlds that connects directly to you in a way you never imagined. The answer is not what science taught you in school. It is stranger than that, more beautiful than that, more personal than that. By the time you reach the final planet, you will understand something about yourself that most people never realize. Something about where you came from, what you are made of, and why you are capable of wonder at all. But first, we have to visit them one by one, starting with the loneliest world in the solar system, the one closest to the sun, the one that knows both fire and ice in ways that should be impossible. 8 worlds spin in the cosmic dark, each one a chapter in a story we are still reading. Tonight we visit them one by one, from fire to ice, from stone to storm, from silence to wind, and somewhere in their secrets lies something about us, something we forgot, or never knew, or have been trying to remember since the first human looked up and wondered what those lights really were. The journey begins at the edge of understanding, at the place where solid ground meets endless mystery. At the first planet, the swift one, the lonely messenger carrying a message nobody has heard in 4 billion years. Hey guys, tonight we begin with a peaceful journey through our solar system, visiting 8 worlds that have been spinning through space long before humans ever looked up. From the scorching surface of Mercury to the frozen blue depths of Neptune, each planet carries stories written in stone, ice, and storm. Facts that feel like cosmic lullabies. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you are tuning in from and what time it is for you. It is always fascinating to see who is joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum, get into your blanket, and let us ease into tonight's journey together. First world we visit is the loneliest. Imagine being closest to warmth, but feeling the coldest. Mercury knows both fire and ice in the same breath, a paradox wrapped in gray stone, spinning slowly at the edge of the sun's fury. Named after the Roman messenger god because it moves fastest across Earth's sky, completing its orbit in just 88 days. But the name carries weight beyond speed. Mercury is a messenger, but the message it carries is one of solitude, of surviving impossible extremes, of being so close to power yet touched by darkness. Mercury is the smallest planet now that Pluto has been reclassified, barely larger than Earth's moon. From Earth, it appears as a bright dot near the horizon just after sunset or before sunrise, never straying far from the sun in our sky. Ancient astronomers thought it was two different objects, a morning star and an evening star, not realizing it was the same world appearing on opposite sides of the sun. The paradox of proximity defines everything about Mercury. You would think being closest to the sun means eternal burning heat, an inferno that never cools. And during the day, that is almost true. When the sun climbs overhead, temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead into liquid pools, hot enough that zinc would boil away. The sun appears 3 times larger from Mercury than from Earth, a massive burning disk dominating the black sky, pouring radiation onto the barren surface with nothing to stop it. But at night, everything changes. When Mercury's slow rotation finally carries a point on the surface away from the sun, temperatures plummet to minus 290 degrees Fahrenheit. Over 1,000-degree difference between day and night, the most extreme temperature swing anywhere in the solar system. One side bakes while the other freezes, and there is no in between, no twilight zone of comfortable warmth, just fire or ice, chosen by which way you face. This happens because Mercury has almost no atmosphere, just a thin exosphere, barely there, made of atoms blasted off the surface by solar wind and micrometeorite impacts. Oxygen, sodium, hydrogen, helium, potassium, all present in trace amounts, but nothing thick enough to trap heat or shield the surface. The vacuum of space presses against bare rock with only the thinnest veil between them. So when the sun sets, the heat radiates directly back into space with nothing to hold it. The ground goes from melting metal to freezing solid in hours. Something strange happens to time on Mercury. It takes 59 Earth days for Mercury to spin once on its axis, but it only takes 88 Earth days to complete one orbit around the Sun. This creates the strangest day-night cycle in the solar system. One day on Mercury, from sunrise to sunrise, lasts 176 Earth days. Almost 2 Mercury years pass during a single Mercury day. The sun crawls across the sky so slowly you could watch it move. Then something bizarre happens. In some locations on Mercury, the sun rises, climbs part way up the sky, stops, reverses direction, and sets again, then rises a second time and continues its path. This happens because Mercury's elliptical orbit carries it faster at certain points, and the orbital speed temporarily exceeds the rotational speed, causing the Sun to appear to move backwards briefly. A cosmic stutter that breaks the rules of dawn. Time itself feels different there, stretched and strange. If you stood on Mercury, you would see a wasteland of memory carved into gray and brown stone. The surface is covered in impact craters from billions of years of bombardment, scars from the violent early solar system when planets were still sweeping up debris. The largest scar is the Caloris Basin, an impact crater 960 miles across, wider than Texas. The collision that created it was so violent that it sent shockwaves through the entire planet. On the opposite side of Mercury from Caloris, the ground buckled and fractured from the seismic waves, creating weird terrain of hills and valleys that scientists call chaotic terrain. One impact literally reshaped the far side of the planet. Between the craters, smooth plains stretch for hundreds of miles, ancient lava flows from a time when Mercury's interior was still molten enough to fuel volcanism. The lava oozed out through cracks and flooded low-lying areas, then froze solid as the planet cooled. But then Mercury itself began to shrink. As the core cooled, the whole planet contracted, its radius decreasing by several miles over billions of years. The crust, already solid, wrinkled like the skin of fruit, left too long in the sun. Massive cliffs called scarps formed, some rising over a mile high and stretching for hundreds of miles, places where the crust buckled and thrust upward as the planet shrank beneath it. Mercury is a world growing old, collapsing slowly inward, wearing its age in wrinkles of stone. Here is the mystery. Within the mystery, the secret Mercury, kept until spacecraft arrived to look closely on the hottest planet in terms of maximum temperature, ice survives. Deep in craters at the north and south poles, where crater walls cast shadows so deep that sunlight has not touched the ground in millions of years, frozen water hides, permanent darkness, permanent cold, even on Mercury. Radar observations from Earth first hinted at it, bright reflections from the polar regions that looked like ice. NASA's Messenger spacecraft confirmed it, detecting hydrogen consistent with water ice, along with darker material that might be organic compounds, carbon-based molecules mixed with the ice. Where did this water come from? Comets? Probably icy bodies from the outer solar system that crashed into Mercury billions of years ago. The ice from the impacts vaporized everywhere except in those permanently shadowed craters where it has remained frozen ever since, a tiny refuge of ice on a world that knows fire. The organic compounds are even stranger, the building blocks of complex chemistry surviving in the last place you would expect to find them. What does it mean that ice and organics exist together on Mercury, hiding in the dark? Mercury has no moon, no companion in the darkness. The sun's gravity is too strong, too jealous to allow a satellite to form or remain in a stable orbit. This close, Mercury orbits alone, just itself and the massive iron core that dominates its interior. That core makes up 85% of the planet's radius, a far higher proportion than any other planet. Mercury is essentially a giant metal ball wrapped in a thin shell of rock. Why so much iron? Theories suggest that early in the solar system's history, a massive impact stripped away much of Mercury's rocky mantle, leaving the iron core exposed with only a thin crust reformed over it. Another act of violence shaping this world. Despite having no molten outer core like Earth, Mercury still has a weak magnetic field, only about 1% the strength of Earth's. Scientists think it comes from a partially liquid outer core, enough motion of molten iron to generate a dynamo effect, just barely. This weak field creates a magnetosphere, a bubble of magnetic protection around the planet, deflecting some of the solar wind, but not much. Charged particles from the sun still bombard the surface, slowly eroding it, atom by atom, over deep time. Humans have sent only 3 missions to Mercury, and reaching it is extraordinarily difficult. You cannot just point a rocket at Mercury and fly straight there. The sun's immense gravitational pull accelerates anything that falls toward it, and slowing down enough to orbit Mercury instead of overshooting or crashing requires enormous amounts of fuel. The solution is gravity assists, using the gravitational fields of other planets as brakes and steering mechanisms. Mariner 10 flew by Mercury 3 times in 1974 and 1975, the first spacecraft to visit, capturing images of a heavily cratered surface that looked like the moon's twin. Messenger became the first spacecraft to orbit Mercury in 2011, spending 4 years mapping the surface, studying the magnetic field, confirming ice at the poles, and revealing Mercury to be far more geologically complex than expected. Bepi Colombo, a joint European and Japanese mission launched in 2018, is now on a 7 year journey to Mercury, using 9 planetary flybys to shed enough velocity to enter orbit. Even our machines struggle to visit the lonely messenger. Mercury teaches about endurance, about surviving extremes, about being close to power but untouched by its benefits, about carrying messages in silence, messages written in stone and ice, in craters and scarps, in the slow rotation that makes time stretch strange. Mercury has been there since the beginning, watching the sun burn, spinning its slow dance, alone. But Mercury's loneliness is nothing compared to what hides on the next world, a place that looks beautiful from far away, the brightest natural object in Earth's sky, after the sun and moon. Ancient people saw it and thought goddess, thought love, thought beauty. They did not know what she was hiding beneath her smile. Venus waits ahead, wrapped in thick clouds, and those clouds hide a secret about what happens when a planet's climate breaks and never recovers. The brightest thing in the sky, after the sun and moon, when Venus appears in the evening, it outshines everything, hanging above the horizon like a jewel suspended in twilight. Ancient people called it the evening star when it followed the sun into darkness, the morning star when it preceded dawn. They thought it was 2 different celestial beings, not understanding they were seeing the same world at different points in its orbit. Every culture that looked up gave Venus special significance. Romans named it after their goddess of love and beauty, captivated by its radiance. They could not have been more wrong about what it really is. Venus is the most beautiful nightmare in our solar system, a cautionary tale wrapped in brilliance. Those thick clouds that make Venus shine so magnificently, reflecting sunlight better than any other planet. They are not soft, they are not gentle, they are a prison made of sulfuric acid, trapping heat beneath them in ways that turned an entire world into hell. Something catastrophic happened to Venus long ago, so violent that it changed the direction of time itself. Venus spins backwards, compared to almost every other world in our solar system. The sun rises in the west and sets in the east, a retrograde rotation that makes no sense unless you understand that Venus was knocked off course. Most scientists believe a massive collision occurred early in the planet's history, an impact with something perhaps the size of a large moon or small planet. The violence was so extreme that it reversed the entire planet's spin. Imagine an object so massive hitting Venus that it stopped the planet's rotation and then started it spinning the other direction. The spin is also impossibly slow. It takes Venus 243 Earth days to rotate once on its axis, but it only takes 225 Earth days to orbit the Sun. A day on Venus is longer than a year, time broken in a different way than Mercury, stretched so thin that the Sun crawls across the sky at a pace you could match by walking. If you stood on Venus, which you could not survive doing, you would watch the Sun creep westward so slowly that it would take 58 Earth days to go from sunrise to sunset, then another 58 days of night before the sun rose again in the west. But you would never see the sun through those clouds anyway. The atmosphere of Venus is so thick that sunlight is scattered and diffused before it reaches the ground. The sky glows with an eerie orange light, sourceless and constant, like being inside a lamp, and that atmosphere is crushing. The pressure at the surface is 92 times greater than Earth's sea level pressure. 92 times. That is equivalent to being 3,000 feet underwater in Earth's oceans. The air is not air, it is more like a fluid, pressing against you from all sides with such force that it would collapse your lungs instantly, crush your rib cage, compress your body until it failed. A human standing on Venus would be flattened before the heat even finished killing them. And the heat. Venus is hotter than Mercury, despite being farther from the sun. The surface temperature is 900 degrees Fahrenheit, hot enough to melt lead into puddles, hot enough to make zinc boil. This heat never varies. Day or night makes no difference. The poles are the same temperature as the equator. The entire planet exists at one constant, unbearable temperature, a uniform inferno from which there is no escape. This is what scientists call a runaway greenhouse effect, and it is the most important warning Venus offers us. The atmosphere is 96% carbon dioxide, a greenhouse gas that traps heat. Sunlight passes through the clouds and atmosphere, strikes the surface, converts to infrared radiation, heat, and then that heat tries to escape back into space. But the carbon dioxide does not let it leave. The thick atmosphere acts like a blanket, trapping the heat, which makes the surface hotter, which radiates more heat, which gets trapped, which makes it hotter still. A feedback loop that reinforced itself over millions of years until the entire planet became an oven with no off switch. Venus was not always like this. Evidence suggests that billions of years ago, Venus might have had liquid water on its surface, oceans that reflected starlight, perhaps even clouds made of water vapor instead of acid. Computer models show that Venus, with a slower rotation and liquid water, could have maintained stable temperatures for perhaps 2 billion years. It sits at the inner edge of the habitable zone, the region around the sun where liquid water can theoretically exist. For a time, Venus might have been habitable, but something tipped the balance. Perhaps volcanic eruptions released too much carbon dioxide. Perhaps the sun grew slightly brighter as it aged. pushing Venus past a critical threshold. Perhaps the slow rotation meant the planet could not generate a strong magnetic field, and solar wind slowly stripped away hydrogen from water vapor in the upper atmosphere, leaving the oxygen to bond with surface rocks and the planet to dry out. Whatever the trigger, once the greenhouse effect started, it fed on itself. Temperatures rose. Oceans began to evaporate. Water vapor is itself a greenhouse gas, so more heat got trapped. The oceans evaporated faster. Eventually, all the water was in the atmosphere, and ultraviolet radiation from the sun broke the water molecules apart. Hydrogen escaped to space. Oxygen reacted with rocks. The oceans vanished forever, boiled away into the cosmos, leaving only the carbon dioxide to thicken and press down and trap heat until Venus became what it is now. The clouds that make Venus so bright are made of sulfuric acid droplets formed when sulfur dioxide from volcanoes reacts with the trace amounts of water vapor that remain. These clouds form a layer 30 miles thick, starting about 30 miles above the surface and extending to 50 miles up. Within this layer, it rains sulfuric acid. Drops form and fall, but they never reach the ground. The heat below is so intense that the acid evaporates mid-air, turning back to vapor before it can touch the surface. An eternal rain that never lands, suspended in the act of falling forever. Lightning flashes constantly in those clouds, not like Earth's lightning, but something stranger, caused perhaps by volcanic ash mixed into the atmosphere or by the chemistry of sulfuric acid clouds generating static charges. The entire planet crackles with electrical activity, a low frequency hum of energy that radio telescopes on Earth can detect. The clouds glow faintly from within, lit by the continuous discharge. Beneath the clouds, the surface is hidden from view, invisible from space, in normal light. Only radar can penetrate the thick atmosphere to map the terrain below. What that radar reveals is a volcanic world, a landscape shaped by lava on a scale hard to comprehend. Vast plains of frozen lava stretch for thousands of miles, smooth and flat, except where they are interrupted by volcanic features. Over 1,600 major volcanoes have been identified, more than any other planet. They range from small domes to massive shield volcanoes, hundreds of miles across. Some of these volcanoes may still be active. Scientists have detected variations in sulfur dioxide levels in the atmosphere that could indicate ongoing eruptions. Certain regions show changes in surface brightness over time, possibly fresh lava flows. Venus is not geologically dead, despite its age. The planet is still reshaping itself through volcanism, adding more gas to the already choking atmosphere. One type of volcanic feature is unique to Venus, found nowhere else in the solar system: pancake domes. These are perfectly circular, flat top domes of lava, some of them 15 miles across, with steep sides and smooth tops like massive stone cylinders. They form when thick, viscous lava oozes out of the ground, too thick to flow far, piling up on itself in symmetrical domes. The low gravity and lack of erosion on Venus allows these structures to remain intact for millions of years, strange monuments to alien geology. There are also coronae, circular features hundreds of miles wide, formed when plumes of hot rock rise from deep in the mantle, pushing the crust upward in huge blisters. When the pressure releases, the center collapses, leaving a circular depression surrounded by ridges and fractures. Over 500 coronae mark Venus's surface, scars from internal heat trying to escape through the thick crust. The surface itself is young by geological standards. The entire planet appears to have been resurfaced about 300 to 600 million years ago, possibly by a global volcanic event that covered the old surface with fresh lava. Before that event, Venus might have looked completely different. But now, the craters that should be there from billions of years of impacts are mostly gone, covered over by lava flows. Only relatively recent craters remain, proof that the surface we see today is not the original surface Venus was born with. Russia, during the Soviet era, succeeded in landing spacecraft on Venus's surface, the only nation ever to do so. The Venera program sent a series of landers, each one built like a tank, heavily armored, designed to withstand pressure and heat that would destroy normal spacecraft in minutes. Venera 7 in 1970 became the first spacecraft to transmit data from the surface of another planet, surviving 23 minutes before failing. Later missions lasted longer, up to about 2 hours, sending back images and chemical analyses before the heat melted their electronics. The images they sent back show a landscape unlike anywhere else: orange and brown rocks, flat plains stretching to a close horizon, the sky above glowing with diffuse light. No sun visible, just omnipresent illumination filtering through the thick clouds high above. The rocks are volcanic basalt, fractured and weathered by the extreme conditions. Some images show layered rocks, possible sediments from an ancient past, though erosion on Venus is chemical rather than mechanical, since there is no wind strong enough at the surface to move particles and no water to carve valleys. The landers are still there, scattered across Venus's surface. Venera 13 and 14, sent in 1982, transmitted the only color images we have from Venus's surface before they too succumbed to the heat. Their metal bodies are slowly being corroded by the atmosphere, dissolving molecule by molecule, but they will remain for thousands of years, monuments to human curiosity dropped into hell. Venus and Earth are twins in size and mass. Venus's diameter is only about 400 miles less than Earth's. Its mass is 81% of Earth's. It has a similar internal structure, probably an iron core, a rocky mantle, a crust. The two planets formed from the same region of the protoplanetary disk, made of the same materials, born at nearly the same time. They should have been sisters, living parallel lives. But one sister became a garden, and the other became an inferno. The difference was subtle at first. Venus is about 30% closer to the Sun than Earth, just 26 million miles closer. That small difference in distance meant slightly more sunlight, slightly higher temperatures. Perhaps that was enough. Perhaps Venus was doomed from the start by its position, destined to eventually tip into runaway greenhouse, or perhaps it was the lack of plate tectonics. Earth's crust is broken into plates that move and shift, diving into the mantle at subduction zones and emerging fresh at mid-ocean ridges. This recycling pulls carbon dioxide out of the atmosphere, traps it in rocks, and stores it in the crust. Plate tectonics acts as a thermostat for Earth, regulating carbon dioxide levels and keeping the climate stable over geological time. Venus does not have plate tectonics. Its crust is a single unbroken shell, stagnant. Carbon dioxide released by volcanoes stays in the atmosphere, never removed, accumulating over billions of years until the greenhouse effect became irreversible. Scientists who study climate change think about Venus often. They think about it when they model Earth's future climate. They think about it late at night when data shows carbon dioxide levels rising faster than predicted, because Venus shows what a runaway greenhouse looks like when nothing stops it. Earth is not Venus, not yet, maybe never, but Venus is a warning about how fragile planetary climates are, how easy it is for feedback loops to spiral out of control, how a world can cross a threshold from which there is no return. There is something profoundly tragic about Venus, a world that might have been beautiful, that might have had oceans and perhaps even the conditions for life, but something tipped the balance and it became a nightmare that cannot wake. Venus spins slowly in the dark, backward and alone, baking under its own trapped heat, a cautionary tale that no one who lived there survived to tell. We leave Venus and its acid clouds behind, grateful that the next world we visit is home, but seeing Earth, after seeing Venus changes everything. After witnessing what can go wrong, we begin to understand how miraculous it is that anything went right. Earth waits ahead, blue and alive, the only world in the universe we know for certain holds life. But the question Venus forces us to ask is how long that will remain true. After Mercury's loneliness and Venus's rage, we come to the third planet, the one that should not exist, not like this, not with liquid water and oxygen and life covering nearly every surface, the statistical anomaly, the world that won a cosmic lottery and then maintained its prize for billions of years. From space, Earth is immediately, strikingly different from every other rocky planet. It is blue, 71% of the surface covered by liquid water oceans that reflect and scatter blue wavelengths of light, white swirls of clouds made of water vapor, always moving, always changing, creating weather patterns that distribute heat from equator to poles, brown and green land masses, continents shaped by tectonic forces, mountains rising, deserts spreading, forests growing, and at night, on the side facing away from the sun, the lights of human civilization glowing in clusters, marking cities and roads, proof of a species that learned to bend the planet to its needs. Earth sits in what scientists call the habitable zone, the region around the sun where temperatures allow liquid water to exist on a planet's surface, not too close like Venus, where water boils away, not too far like Mars, where it freezes solid, just right, a Goldilocks position that makes liquid water possible. But being in the habitable zone is not enough. Mars is in the habitable zone, and it is a frozen desert. The habitable zone gives you a chance, nothing more. What you do with that chance depends on 1,000 other factors aligning perfectly. Earth's distance from the Sun is 93 million miles, a distance so commonly referenced in astronomy. It has its own unit, the astronomical unit, or AU. 1 AU is the baseline for measuring everything else. Venus is 0.7, 2 AU. Mars is 1.5, 2 AU. At 1 AU, Earth receives about 1,360 watts of solar energy per square meter, enough to warm the surface to an average temperature of 59 degrees Fahrenheit. Not too hot, not too cold, right in the range where water stays liquid, where complex chemistry can occur, where life can emerge and thrive. But this balance is maintained by something invisible, something most people never think about: Earth's magnetic field. Deep beneath the surface, about 1,800 miles down, Earth's outer core churns in constant motion. This outer core is liquid iron and nickel, heated to over 9,000 degrees Fahrenheit by the decay of radioactive elements and the residual heat from Earth's formation. The inner core, even deeper, is solid iron, kept solid despite the heat by the immense pressure of all the rock above it. The temperature at the inner core is about 10,800 degrees Fahrenheit, as hot as the surface of the sun. The liquid outer core does not sit still. It flows in complex patterns, driven by heat rising from below and Earth's rotation creating Coriolis effects. This flow of electrically conductive liquid metal generates electric currents, and those currents generate a magnetic field, the same principle that powers an electromagnet or a dynamo. The magnetic field extends thousands of miles into space, creating a protective bubble called the magnosphere. This magnetosphere saves Earth. The sun constantly emits a stream of charged particles called the solar wind, electrons and protons blasted outward at over 1 million miles per hour. When these particles hit Earth's magnetic field, they are deflected around the planet, flowing past like water around a rock in a stream. Some particles get funneled toward the poles where the magnetic field lines converge, and when they collide with oxygen and nitrogen in the upper atmosphere, they create auroras, the northern and southern lights, curtains of green and red and purple light, shimmering above the Arctic and Antarctic. Without the magnetosphere, the solar wind would hit Earth's atmosphere directly, slowly stripping it away over millions of years. Oxygen and nitrogen molecules would be broken apart by radiation, ionized, and swept off into space. Earth would lose its air the same way Mars did. Mars had a magnetic field once, generated by a molten core, but the core cooled and the dynamo stopped. The magnetic field collapsed. Solar wind stripped away most of Mars's atmosphere over the next billion years. Mars went from a potentially habitable world with liquid water to a frozen desert with air pressure less than 1% of Earth's. The lack of a magnetic field killed Mars. Earth avoided that fate because it is large enough that its core is still hot, still molten, still generating the field that protects us. Size matters in planetary survival. Earth's mass is enough to keep the internal heat from dissipating too quickly. The magnetic field is not permanent. Eventually, billions of years from now, Earth's core will cool and the field will weaken and vanish. But that is so far in the future that the sun will have expanded into a red giant and consumed the planet long before the magnetic field fails. The atmosphere itself is another miracle: 78% nitrogen, 21% oxygen, trace amounts of argon, carbon dioxide, water vapor, and other gases. But the composition we have now is not the composition Earth started with. The original atmosphere was mostly hydrogen and helium, the lightest elements captured from the solar nebula, but Earth's gravity was not strong enough to hold on to those light gases, and solar wind blew them away. A second atmosphere formed from volcanic outgassing, carbon dioxide, and water vapor and nitrogen released from the interior as the young planet's surface churned with volcanic activity. This atmosphere was thick with carbon dioxide, more like Venus. Then something extraordinary happened. Life emerged. Single-celled organisms appeared in the oceans about 3.7 billion years ago, maybe earlier, we are not certain. For over a billion years, these microbes lived in oceans, metabolizing chemicals, evolving, diversifying. Then, about 2.4 billion years ago, some of these microbes developed photosynthesis, the ability to use sunlight to convert carbon dioxide and water into sugar and oxygen. Oxygen was a waste product for them, released into the water and eventually into the atmosphere. This event, called the Great Oxidation Event, fundamentally transformed Earth. Oxygen is reactive. It rusts iron, oxidizes rocks, and in high concentrations, it is toxic to life forms that evolved without it. Many of the early anaerobic organisms died in what might be the first mass extinction, poisoned by oxygen, but oxygen also enabled new forms of life. Aerobic organisms that used oxygen for metabolism could extract far more energy from food than anaerobic ones. Complex multicellular life became possible. Animals evolved, plants colonized land. The entire biosphere exploded in diversity, all because microbes started producing oxygen as waste. The oxygen we breathe exists only because of life. Take away the life, and the oxygen would disappear in a few million years, reacting with rocks and volcanic gases until it was all bound up in minerals. Earth's atmosphere is maintained in a state of chemical disequilibrium by living organisms. The air itself is alive, constantly refreshed, a product of the biosphere. Earth also has one large moon, unusually large for a planet of Earth's size. The moon formed from violence about 4.5 billion years ago, roughly 50 million years after the solar system formed. A Mars-sized protoplanet named Theia collided with the young Earth. The impact was so catastrophic that it vaporized both objects' outer layers, sending a huge amount of debris into orbit. This debris, molten rock and metal, formed a ring around Earth. Over time, the ring material coalesced under its own gravity, forming the moon. The moon is not just a pretty light in the night sky. It plays a crucial role in Earth's stability. The moon's gravity creates tides in Earth's oceans, the water rising and falling as the moon orbits. These tides dissipate energy, slowing Earth's rotation very gradually. A day on early Earth was only about 6 hours long. Over billions of years, tidal friction has lengthened the day to 24 hours, and the process continues. The moon is slowly drifting away from Earth at about 1.5 inches per year as it gains the angular momentum that Earth loses. More importantly, the moon stabilizes Earth's axial tilt. Earth's axis is tilted 23.5 degrees relative to its orbital plane, and this tilt is what creates seasons. Summer and winter happen because the tilt causes one hemisphere to receive more direct sunlight at certain times of year, while the other receives less. But without the moon's gravitational influence, Earth's axis would wobble chaotically over millions of years due to gravitational perturbations from other planets. The tilt could vary from 0 degrees, no seasons at all, to 85 degrees, extreme seasons where the poles face the sun directly. This would create wild climate swings, making it difficult for complex life to adapt. The moon keeps Earth's tilt stable, giving us consistent seasons, predictable climate, a steady environment in which life can flourish. Water covers most of Earth's surface, but water is strange. It should not be liquid at Earth's distance from the sun, given the amount of solar heating alone. Liquid water exists because of the greenhouse effect, but a natural, balanced greenhouse effect, not the runaway version that consumed Venus. Carbon dioxide and water vapor in the atmosphere trap some of the sun's heat, raising the surface temperature by about 60 degrees Fahrenheit compared to what it would be without an atmosphere. This keeps the oceans liquid, the water cycle running, the climate habitable. The oceans are not evenly distributed. The Pacific Ocean alone covers nearly half the planet's surface. The Atlantic, Indian, Southern, and Arctic oceans fill most of the rest. These oceans are connected, forming one global ocean with currents that circulate water and heat around the planet. Warm water flows from the equator toward the poles. Cold water sinks and flows back toward the equator. This thermohaline circulation acts like a conveyor belt, distributing heat, moderating temperature extremes, making Earth's climate far more stable than it would be otherwise. The deepest parts of the ocean drop to over 36,000 feet, 7 miles down in the Mariana Trench. At these depths, pressure exceeds 15,000 pounds per square inch, enough to crush most materials, yet life exists even here. Strange creatures adapted to the dark and cold and pressure, living near hydrothermal vents, where superheated water rich in minerals erupts from cracks in the seafloor. These ecosystems do not depend on sunlight at all. They run on chemosynthesis, microbes converting chemicals from the vents into energy, forming the base of a food chain in eternal darkness. Most of the ocean floor has never been directly observed by humans. We have better maps of Mars's surface than of Earth's ocean floor. The deep sea remains one of the last unexplored frontiers on our own planet, holding who knows how many undiscovered species, geological features, ecosystems we have never imagined. Life on Earth exists in extraordinary diversity. Scientists have cataloged about 1.7 million species so far, but estimates suggest the true number might be 8 million, 10 million, maybe more. Life has adapted to every available niche, from bacteria living miles underground in solid rock to birds flying at 30,000 feet, from fish in Antarctic waters, cold enough to freeze other creatures, to microbes in hot springs at near boiling temperatures. Life fills every space, exploits every resource, creates ecosystems of staggering complexity. All of this life is connected through cycles. The water cycle lifts water from oceans through evaporation, carries it over land as clouds, drops it as rain, returns it to oceans through rivers. The carbon cycle moves carbon through atmosphere, oceans, life, and rocks. The nitrogen cycle converts atmospheric nitrogen into forms usable by plants. Every element necessary for life cycles through the biosphere, used and reused, recycled endlessly. We are living through a time of rapid change. Earth's climate has always varied naturally, ice ages alternating with warmer periods, driven by changes in Earth's orbit, volcanic eruptions, shifts in ocean circulation. But something unprecedented is happening now. Human activity, primarily burning fossil fuels, has increased atmospheric carbon dioxide from 280 parts per million before the Industrial Revolution to over 420 parts per million today. This is enhancing the greenhouse effect, trapping more heat, raising global temperatures faster than natural variation can explain. The last time carbon dioxide levels were this high was over 3 million years ago, during the Pliocene epoch, when global temperatures were several degrees warmer and sea levels were 50 feet higher. We are conducting an experiment on our own atmosphere, pushing it toward a state Earth has not experienced since long before humans existed. The consequences are already visible. Ice sheets in Greenland and Antarctica are melting faster than predicted. Glaciers worldwide are retreating. Sea levels are rising. Weather patterns are shifting. Species are going extinct at rates not seen since the dinosaurs died 66 million years ago. This is Earth's sixth mass extinction event, but the first caused by a single species. For 5 times before, Earth's biosphere has suffered catastrophic collapses that killed most living species. The Permian extinction, 252 million years ago, killed 96% of marine species. The Cretaceous extinction, 66 million years ago, triggered by an asteroid impact, killed the non-avian dinosaurs. Each time life recovered, but recovery took millions of years. We are living through the opening act of the next one, driven not by asteroids or volcanoes, but by our own success as a species. Yet here is the deepest truth about Earth, the realization that changes everything once you understand it. You are not on Earth. You are Earth. Every atom in your body was once part of this planet. The calcium in your bones came from rocks dissolved in ancient seas. The iron in your blood was forged in a supernova explosion billions of years before the sun existed. The carbon in your cells cycled through countless living things before becoming you. The water in your body fell as rain, flowed through rivers, evaporated from oceans, over and over for 4 billion years. You are made of earth, assembled from its elements, animated by chemical reactions that Earth's environment makes possible. You breathe oxygen produced by plants and algae. You drink water purified by the planet's hydrological cycle. You eat food grown in soil made from weathered rock and decomposed organisms. You are not separate from Earth. You are a temporary pattern that Earth has made from itself, a way for the planet to experience consciousness, to look back at its own history, to ask questions about where it came from and where it is going. This is what the planets have been trying to tell us. We are not observers standing apart from nature. We are nature becoming aware of itself. The same processes that formed Mercury and Venus and Mars formed Earth. The same stardust, the same physics, but here the conditions aligned in just the right way, and matter organized itself into life, and life organized itself into minds, and minds started asking why. After seeing the loneliness of Mercury, the nightmare of Venus, we realize how improbable this is. How many things had to go right? The right distance from the sun, the right size to hold an atmosphere and maintain a magnetic field, the right amount of water delivered by comets, the emergence of plate tectonics to regulate carbon, the impact that formed the moon to stabilize the tilt, the development of photosynthetic life to create oxygen, every step necessary, every step unlikely, yet all of them happened here. Earth is rare. We have found thousands of exoplanets around other stars, and some of them orbit in habitable zones, but we do not know yet if any of them have conditions like Earth's. We do not know if life is common or vanishingly rare. We might be one of billions of living worlds in the galaxy, or we might be the only one until we find another. Earth is the only place in the universe we know for certain holds life. We leave Earth reluctantly, carrying the weight of that knowledge. The next world waits ahead, red and dusty and quiet, a planet that almost made it, that had water and a thick atmosphere once, but lost them both. Mars holds secrets about what Earth might have been, or what it might become if something goes wrong. The red planet remembers, and its memories are written in stone and ice. Fourth planet from Sun, painted red with rust, iron oxide covering every surface like dried blood, giving Mars its distinctive color visible from Earth, even with the naked eye. Ancient people saw that red light moving against the fixed stars and thought of war, of blood, of conflict. Romans named it after their god of war, Mars. But Mars is not a warrior. Mars is a ghost, a world that remembers what it used to be, when rivers carved valleys through stone and oceans might have lapped at ancient shores billions of years ago. From orbit, you can see the evidence of water everywhere. It is undeniable, written in the landscape itself. River valleys snake across the surface, channels carved by flowing water, branching tributaries, joining main channels just like river systems on Earth. Some of these valleys are thousands of miles long, cutting through ancient terrain, proof that water flowed here for extended periods, not just brief floods, but sustained rivers that ran for thousands or millions of years. Deltas spread out where rivers once emptied into larger bodies of water, sediment deposited in fan shapes exactly like deltas on Earth. Dry lake beds cover vast areas, some of them thousands of square miles across, flat plains of sediment that settled out of standing water. The northern lowlands of Mars show features consistent with an ancient ocean, a body of water that might have covered a third of the planet's surface. The boundary between the highlands and lowlands has the appearance of an ancient shoreline, though debate continues about whether it truly was an ocean or just a series of large lakes. Minerals tell the same story. Sorbiters and rovers have identified clay's hematite sulfates minerals that form only in the presence of liquid water. Clays require water to alter volcanic rock over long periods. Fumatite deposits suggest water-rich environments. Sulfates form when water evaporates, leaving dissolved minerals behind. The mineralogy of Mars is a record of water's presence, chemical evidence that the planet was once wet. Mars had a thick atmosphere once, thick enough to keep water liquid on the surface, despite Mars being farther from the Sun than Earth. Greenhouse gases, probably carbon dioxide and water vapor, trapped heat and maintained temperatures above freezing at least some of the time. Rain fell from clouds. Snow accumulated at higher elevations. The hydrological cycle operated, water moving between surface and atmosphere, just like on Earth. Then something catastrophic happened. Mars lost its magnetic field. Early in its history, Mars had a global magnetic field like Earth's, generated by a liquid iron outer core. But Mars is smaller than Earth, about half the diameter, one-tenth the mass. Smaller planets cool faster. Mars's core cooled and solidified more quickly than Earth's. The dynamo that generated the magnetic field shut down, probably within the first billion years of Mars's existence. Without the magnetic field's protection, the solar wind hit Mars's atmosphere directly. Charged particles from the sun struck air molecules, ionizing them, stripping electrons away, and the solar wind then swept these ionized particles off into space. Slowly, over hundreds of millions of years, Mars bled its atmosphere into the void. The atmospheric pressure dropped. As pressure decreased, Liquid water became unstable. Water either evaporated into space or froze into the ground. The rivers stopped flowing. Lakes dried up. If there was an ocean, it vanished, either lost to space or frozen beneath the surface. Mars today has an atmosphere only about 1% as thick as Earth's, too thin to support liquid water, too thin to block much radiation, too thin to retain heat. The average surface temperature is minus 80 degrees Fahrenheit, far below water's freezing point. At the equator on a summer day, temperatures can reach 70 degrees Fahrenheit, warm enough for liquid water, but the atmospheric pressure is so low, about 600 pascals compared to Earth's 101,000 pascals, that liquid water would immediately boil away. Mars exists in a state where water can only be ice or vapor, never liquid on the surface. But Mars still holds on to grandeur. Olympus Mons rises from the Tharsis Plateau, the largest volcano in the entire solar system. It towers 13 miles above the surrounding plains, 3 times the height of Mount Everest, with a base 374 miles across. If you stood on Mars and looked at Olympus Mons, you could not see the whole thing. The base would curve beyond the horizon in every direction. The summit would be too distant to see from the base. It is so massive that if you climbed it, you would not realize you were climbing a mountain. The slope is so gradual, averaging only about 5 degrees, that it would feel like walking across gently rising plains. Only after walking for days would you realize you had climbed miles into the sky. Olympus Mons is a shield volcano formed by lava flowing steadily from a central vent and spreading out in thin layers over millions of years. On Earth, shield volcanoes like those in Hawaii are limited in size by plate tectonics. The crust moves, carrying the volcano away from its magma source, and a new volcano forms. But Mars has no plate tectonics. The crust is a single stationary shell. A volcano on Mars can sit over the same hot spot for billions of years, erupting again and again, building up layer after layer of lava until it reaches truly colossal size. Olympus Mons is not alone. The Tharsis region contains 3 other giant volcanoes, Asclepius Mons, Pavonis Mons, and Arsia Mons, all over 9 miles high. These 4 volcanoes erupted for billions of years, pouring out so much lava that they created the Tharsis Bulge, a raised region the size of North America, lifting the Martian surface several miles higher than the surrounding terrain. The weight of Tharsis stressed the crust, causing it to crack, and those cracks became the source of another of Mars's most dramatic features. Valles Marineris cuts across Mars like a wound, a canyon system stretching 2,500 miles along the equator. It is 4 times deeper than the Grand Canyon, in places dropping 6 miles from rim to floor. The canyon is so vast that it would span the entire width of the United States if placed on Earth. 1/5 of Mars's circumference is scarred by this immense rift. Valles Marineris probably formed when the Tharsis Bulge rose, cracking the crust around it, like dried mud cracks when it shrinks. Tectonic forces pulled the surface apart, creating a rift valley. Water may have widened it later, flowing through the cracks, eroding the walls, carving tributary canyons. Landslides, some of the largest in the solar system, collapsed the canyon walls in places, creating debris fields miles across. The canyon's floors show layered rock, sediments that might have been deposited by water or wind, or both. Valles Marineris is a geological treasure, a cross-section through billions of years of Martian history, exposed in its walls. At both of Mars's poles, ice caps gleam white against the red surface. These polar ice caps are made of two kinds of ice: water ice and frozen carbon dioxide, dry ice. In winter, carbon dioxide from the atmosphere freezes out onto the poles, coating them in dry ice several feet thick. In summer, the dry ice sublimates back into the atmosphere, and the permanent water ice caps are revealed beneath. The northern cap is larger, about 600 miles across and up to 2 miles thick in places. The southern cap is smaller but still substantial. Both caps show spiral patterns, swirling troughs carved by wind and sublimation over thousands of years, creating features unlike anything on Earth. Beneath the visible ice caps and scattered across the Martian surface, radar instruments on orbiting spacecraft have detected massive amounts of frozen water. Glaciers buried under layers of dust and rock, ice filling the pore spaces in soil and rock to depths of hundreds of feet. If all the ice on Mars were melted, there would be enough water to cover the entire planet in a liquid ocean about 100 feet deep. Mars has not lost all its water. Most of it is still there, locked away in frozen reservoirs, waiting. Mars has two small moons, Phobos and Deimos, Fear and Panic, named after the attendants of the war god in Greek mythology. Both are irregularly shaped, more like potatoes than spheres, heavily cratered, dark gray, almost black. They are probably asteroids captured by Mars's gravity early in the solar system's history, pulled from the asteroid belt and forced into orbit. Phobos is the larger of the two, about 17 miles across at its widest, and it orbits incredibly close to Mars, only 3,700 miles above the surface. It completes an orbit in just 7.5 hours, circling Mars 3 times each Martian day. From the surface, Phobos rises in the west and sets in the east a few hours later, moving visibly across the sky, growing and shrinking as it passes overhead. But Phobos is doomed. Tidal forces between Mars and Phobos are slowing the moon down, stealing its orbital energy, causing it to spiral inward at about 6 feet per century. In roughly 50 million years, Phobos will reach the Roche limit, the distance at which Mars's gravity will overcome Phobos's own gravity, holding it together. The moon will break apart, torn into fragments by tidal forces, and those fragments will spread out into a ring around Mars. For a few million years, Mars will have a ring system, perhaps even more spectacular than Saturn's for its brief existence. Then the ring material will gradually fall into Mars's atmosphere and burn up. Phobos is temporary, counting down its final orbits. Deimos orbits farther out, about 14,500 miles from Mars, completing an orbit every 30 hours. It is slowly drifting away from Mars, gaining energy, while Phobos loses it, eventually escaping Mars's gravity entirely and becoming its own small planet orbiting the Sun. Even Mars's moons are leaving it. The atmosphere that remains on Mars is thin but not empty. It is 95% carbon dioxide, with traces of nitrogen, argon, oxygen, and water vapor. The sky during the day appears butterscotch or peachy colored, a light reddish tan from fine dust suspended permanently in the air. But at sunset, something beautiful and strange happens. The sky turns blue around the sun, the opposite of Earth, where the sky is blue during the day and red at sunset. On Mars, the dusty atmosphere scatters blue light forward toward the sun, while red light scatters in all directions. So when you look toward the sun at twilight, you see blue, and when you look away, you see red. Dust storms are common on Mars, sometimes growing to engulf the entire planet. These global dust storms can last for months, blocking sunlight, dropping temperatures, creating conditions that would shut down any solar powered equipment on the surface. The 2018 global dust storm killed NASA's Opportunity rover after 15 years of operation, covering its solar panels in dust and starving it of power. The storms begin when seasonal heating warms one hemisphere, causing winds to pick up dust. Once airborne, the dust absorbs more sunlight, heating the air, creating stronger winds, lifting more dust, a feedback loop that can spread dust around the planet in weeks. Eventually, the dust settles and the clear skies return, but for a time, Mars vanishes into a red haze. The search for life on Mars is one of the driving questions behind every mission sent there. Did life ever emerge when water flowed on the surface billions of years ago? Ancient Mars had conditions that seem favorable: liquid water, organic molecules delivered by meteorites, energy from the sun and from geothermal sources. On Earth, life appeared relatively quickly once conditions allowed, within the first few 100 million years after the planet cooled enough to have liquid water. If life emerges easily when conditions are right, then Mars should have had life too. We have not found it yet, but we are looking. Rovers have drilled into rocks, analyzed soil, searched for organic molecules. Curiosity and perseverance. Rovers are exploring ancient lake beds and river deltas, places where water once pooled and sediments accumulated, ideal locations for preserving fossils, if any existed. Organic molecules have been detected, carbon-based compounds, but whether they are from biological or geological sources remains unclear. Methane has been detected in the Martian atmosphere in small amounts, appearing and disappearing in seasonal patterns. On Earth, most methane is produced by life, by microbes, in swamps, or inside animals. But methane can also come from geological processes, serpentinization of rocks, reacting with water. The methane on Mars could be from ancient microbes still surviving deep underground, metabolizing slowly in pockets of liquid water beneath the surface, releasing methane that seeps upward. Or it could be geological, nothing to do with life at all. We do not know yet. The possibility that life exists on Mars today, not as a fossil but as living organisms, focuses on the subsurface. The surface is bathed in ultraviolet radiation from the sun, with no ozone layer to block it. Cosmic rays bombard the ground. Perchlorates in the soil are toxic to most life, but underground, conditions might be different. Liquid water could exist where geothermal heat warms the ice, creating briny pockets that remain liquid despite the cold. Microbes could survive there, extremophiles adapted to darkness and cold and high salt concentrations, living in tiny refuges scattered through the Martian crust. This is speculation, but it is grounded in what we know about life on Earth, which has been found in nearly every environment we have looked, no matter how extreme. Mars is the most explored planet in our solar system besides Earth. Dozens of missions have been sent, orbiters mapping the surface in exquisite detail, landers and rovers touching down to study rocks and soil directly. Every mission reveals Mars to be more complex than expected. What seemed like a dead, unchanging world turns out to have active geology, seasonal changes, dust devils dancing across plains, avalanches tumbling down crater walls in spring as carbon dioxide ice sublimates, gullies that might form from briny water flowing briefly down slopes during warm periods. Mars is not frozen in time. It is still changing, still active, just on a slower, quieter scale than Earth. Humans plan to go to Mars. Not just robots, but people walking on the red sand, looking at the sky, experiencing another world firsthand. The challenges are immense. The journey takes 6 to 9 months with current propulsion technology, exposing astronauts to radiation from cosmic rays and solar flares without Earth's magnetic field to protect them. Mars's atmosphere is too thin to breathe, requiring life support systems. The cold would kill an unprotected human in minutes. The soil contains perchlorates that are toxic. There is no food, no breathable air, no liquid water on the surface. Everything needed to survive would have to be brought from Earth or manufactured on Mars. Yet the dream persists. Space agencies and private companies are developing plans, building rockets, testing habitats. The idea is not just to visit Mars, but to stay, to build a permanent human presence, perhaps even terraform the planet over centuries or millennia, releasing the frozen carbon dioxide from the poles to thicken the atmosphere, warming the planet, melting the subsurface ice, bringing back the rivers and lakes. It would take enormous effort, technology we do not fully have yet, timescales spanning generations, but it is theoretically possible. Mars could become a second home for humanity, not a replacement for Earth, but a backup, a refuge, a new world to explore and settle. The ghost of what Mars used to be could become a vision of what it might be again, transformed by the descendants of the species that first looked up at the red light in Earth's sky and wondered what it was. There is something heartbreaking about Mars. It almost made it. It had what Earth has: water, atmosphere, the right conditions. But physics is not kind. Small planets cool faster. Without the size to maintain a molten core, Mars lost its magnetic field. Without the magnetic field, it lost its atmosphere. Without the atmosphere, it lost its water. Everything that made it potentially habitable vanished, not through any fault of Mars itself, but because it was too small to hold on to what it had. Mars is a reminder that being in the habitable zone is not enough. You need the right size to keep your core molten. You need plate tectonics to regulate carbon. You need a magnetic field to keep your atmosphere. You need moons to stabilize your tilt. You need luck, an enormous amount of luck, for everything to align correctly and stay aligned for billions of years. Mars got close, but not quite close enough. It is a world of what ifs and might have beens, frozen in a moment between being alive and being dead, still holding traces of its past, still offering mysteries about what happened and whether life ever walked its shores. We leave Mars and its fading dreams behind and cross an invisible boundary, beyond the asteroid belt where a planet tried to form but failed, scattered into a million rocky fragments by Jupiter's overwhelming gravity. We enter the realm of the giants, worlds so massive they dwarf everything we have seen so far. Planets made not of rock, but of gas and liquid, with no solid ground to stand on, atmospheres thousands of miles deep, storms larger than Earth. The first giant waits ahead, pulling us toward it, with gravity so immense it shapes the entire outer solar system. Jupiter the King, ancient and powerful, surrounded by moons that are worlds unto themselves. The inner solar system of stone and rust and memory gives way to something grander, stranger, more violent. We are entering the domain where physics operates on scales that make planets like Earth seem small, fragile, temporary, where storms rage for centuries and magnetic fields span millions of miles and moons hide oceans beneath ice. Everything changes past the asteroid belt. The inner solar system is made of stone and metal, worlds you could theoretically stand on if you could survive the conditions. But out here, the rules shift. Worlds are made of gas and mystery, substances that transition from vapor to liquid to exotic states under pressures we can barely recreate in laboratories. Jupiter rises before us like a god, and the name fits perfectly. Fifth planet from the Sun, largest in our solar system, named after the king of the Roman gods, because nothing else in our neighborhood commands such overwhelming presence. Jupiter is not just big. The word fails to capture the scale. You could fit 1,300 Earths inside Jupiter's volume. Every other planet in our solar system combined would still fit inside Jupiter with room left over. Its mass is 318 times Earth's mass, 2.5 times more massive than all other planets combined. When you look at the solar system's total planetary mass, Jupiter represents 71% of it. The Sun and Jupiter together account for 99.9% of all the mass in the solar system. Everything else, all the other planets, all the moons, all the asteroids and comets, is essentially rounding error compared to these two giants. But here is the strange part that fundamentally changes what Jupiter is. It has no surface to stand on, no boundary where gas ends and solid ground begins. Jupiter is made primarily of hydrogen and helium, the lightest and most abundant elements in the universe, the same materials that make up the sun and stars. If you fell into Jupiter, you would descend through layers of clouds, ammonia ice crystals giving way to ammonium hydrosulfide clouds, then water clouds, deeper still. The temperature and pressure would increase as you fell. The gas would grow thicker, denser, more liquid than gaseous. Eventually, thousands of miles down, the pressure would become so extreme that hydrogen stops behaving like a gas or even a normal liquid. It transitions into metallic hydrogen, a state where hydrogen atoms are crushed so close together that electrons break free and flow like electricity through metal. An ocean of metallic hydrogen, thousands of miles deep, conducting electricity, generating the most powerful magnetic field of any planet. At the very center, perhaps 10 to 20,000 miles down, there might be a core of rock and ice, heavier elements that sank to the middle during Jupiter's formation. Or perhaps there is no distinct core at all, just a gradual transition from metallic hydrogen to a dense soup of heavier elements. Nobody knows for certain what lies at Jupiter's heart. The pressure there exceeds anything we can measure directly, perhaps 100 million times Earth's atmospheric pressure. The temperature reaches around 43,000 degrees Fahrenheit, hotter than the surface of the sun, though not hot enough to sustain nuclear fusion. Jupiter radiates more heat than it receives from the sun, still cooling from its formation 4.5 billion years ago, slowly releasing gravitational energy as it very gradually contracts. The most famous feature on Jupiter is the Great Red Spot, a storm that has been raging for at least 190 years since it was first reliably observed in the 1830s, though sketches from the 1660s may show it, meaning it could be over 350 years old. This is not a storm in the way Earth has storms. It is an anticyclone, a high pressure system where winds spiral counterclockwise in the southern hemisphere. The spot is currently about 10,000 miles across, large enough to swallow Earth with room to spare, though it has been shrinking. Historical records show it was over 25,000 miles across in the late 1800s. The winds at its edge reach 400 miles per hour, faster than the strongest hurricanes on Earth. Why has it lasted so long? On Earth, hurricanes dissipate when they make landfall because friction with the ground slows them down and they lose their energy source. But Jupiter has no land. The Great Red Spot floats in a zone between two jet streams, moving in opposite directions, and the wind shear from those jets actually feeds energy into the storm, sustaining it. The spot also sits at a latitude where smaller storms from the north and south sometimes collide with it, and the Great Red Spot simply absorbs them, consuming other storms to maintain itself. It is a monster that feeds on chaos. The color is a mystery. Scientists believe it comes from complex organic compounds created when sunlight breaks apart methane and ammonia in Jupiter's upper atmosphere, producing hydrocarbons that then react to form colored molecules. Sulfur and phosphorus compounds might also contribute. The exact chemistry remains uncertain. The brick red color seems to deepen when the spot is growing and fades when it shrinks. The Great Red Spot is not just a storm, it is a chemical laboratory floating in Jupiter's clouds, creating compounds through photochemistry that we do not fully understand. Jupiter's magnetic field is a monster of a different kind. It is the strongest planetary magnetic field in the solar system, about 20,000 times stronger than Earth's. The field extends millions of miles into space, creating a magnetosphere so vast that if we could see it from Earth with our eyes, it would appear several times larger than the full moon in our sky. The magnetosphere is generated by the flow of metallic hydrogen in Jupiter's interior, conducting electricity and creating currents that produce the magnetic field through dynamo action, the same principle as Earth, but on a scale thousands of times more powerful. This enormous magnetic field traps charged particles, electrons, and ions from the solar wind and from volcanic eruptions on Jupiter's moon Io. These particles become trapped in radiation belts around Jupiter, accelerating to nearly the speed of light, creating the most intense radiation environment around any planet. The radiation near Jupiter is so extreme it would kill a human in hours and destroy unshielded electronics in days. Every spacecraft that visits Jupiter must be specially hardened against radiation, with sensitive electronics protected in titanium vaults. The magnetic field also creates the most powerful auroras in the solar system. On Earth, auroras occur when charged particles from the sun follow magnetic field lines to the poles and collide with oxygen and nitrogen in the upper atmosphere, creating green and red light. Jupiter's auroras operate similarly, but on a scale that makes Earth's look tiny. Jupiter's auroras extend thousands of miles above the cloud tops, bright enough to see from Earth with ultraviolet telescopes. They form complete rings around both poles, constantly glowing, fed by the continuous stream of particles from Io's volcanoes and from Jupiter's own magnetosphere. The energy released by Jupiter's auroras is greater than all the energy humanity has ever generated combined. Jupiter's atmosphere is organized into bands of color, light colored zones alternating with dark colored belts, running parallel to the equator. The zones are regions where gas is rising, cooling, forming high altitude clouds of ammonia ice that appear white or cream colored. The belts are regions where gas is sinking. The clouds are at lower, warmer altitudes, and we see deeper into the atmosphere where organic compounds create tan and brown colors. The boundary between zones and belts is violent, wind shear reaching hundreds of miles per hour, creating turbulence and storms that can last for decades. These jet streams exist because of Jupiter's rapid rotation. Despite its enormous size, Jupiter spins faster than any other planet. A day on Jupiter lasts only 9 hours and 56 minutes. This rapid rotation creates powerful Coriolis forces that organize winds into bands running east and west. On Earth, rotation creates similar effects, but our land masses disrupt the flow. Jupiter has no land. The winds can race around the planet endlessly with nothing to slow them down. Some of Jupiter's jet streams reach sustained speeds of 400 miles per hour, wind that never stops, never weakens, flowing for millions of years. The rapid rotation also causes Jupiter to bulge significantly at its equator and flatten at its poles. The planet is not a perfect sphere. The equatorial diameter is about 7% larger than the polar diameter, 88,846 miles, versus 83,082 miles. You can see this ablateness just by looking at Jupiter through a telescope, the planet noticeably squashed. It looks like a ball of clay spinning on a potter's wheel, centrifugal force pulling the equator outward while the poles compress inward. Lightning on Jupiter dwarfs anything on Earth. Voyager spacecraft detected lightning flashes when they flew past in 1979, bright spots deep in the clouds, releasing enormous amounts of energy. Juno spacecraft, which has been orbiting Jupiter since 2016, mapped lightning in detail and found that most of it occurs at the poles, unlike Earth where lightning is most common at the equator. Jupiter's lightning bolts are massive, individual flashes releasing energy equivalent to thousands of terrestrial lightning strikes, illuminating areas larger than Earth. The thunder from such lightning would be deafening if there were anyone to hear it, shock waves propagating through the thick atmosphere. The constant electrical activity creates radio emissions that ham radio operators on Earth can detect, Jupiter broadcasting its presence across the solar system. Jupiter does not rule alone. It has at least 95 confirmed moons, a system unto itself, a miniature solar system orbiting the planet. 4 of these moons are large enough to be considered worlds in their own right. Galileo Galilei discovered them in 1610, the first objects found orbiting something other than Earth, proving that not everything in the cosmos circles around us. These 4, Io, Europa, Ganymede, and Callisto, are called the Galilean moons in his honor. Io is the innermost of the 4, and it holds the title of most volcanically active body in the entire solar system. Its surface is covered in sulfur and sulfur dioxide, giving it yellow, orange, red, and white coloring like a cosmic pizza, as one scientist famously described it. Io has over 400 active volcanoes. At any given moment, several are erupting, shooting plumes of sulfur and sulfur dioxide 300 miles above the surface, far higher than any eruption on Earth. The The plumes freeze in the cold vacuum of space and fall back down, constantly resurfacing Io. Because of this continuous volcanic activity, Io has no impact craters. Every crater that forms is quickly erased by fresh lava flows and volcanic deposits. Why is Io so active? Tidal heating. Io orbits very close to Jupiter, and Jupiter's immense gravity pulls on Io with tremendous force. But Europa, the next moon out, also pulls on Io, creating a gravitational tug of war. This forces Io's orbit to remain slightly elliptical rather than circular. As Io moves closer to and farther from Jupiter during each orbit, the strength of Jupiter's gravitational pull varies, squeezing and stretching Io like a stress ball. This constant flexing generates enormous internal friction, melting Io's interior, keeping it molten despite being far from the sun. Io is being perpetually destroyed and recreated, a world in constant agony and rebirth, torn apart by gravitational forces it cannot escape. Europa is the second Galilean moon and one of the most exciting places in the solar system for the search for life. Europa is covered in a smooth shell of water ice, crisscrossed with cracks and ridges, but remarkably few craters. The surface is young, constantly renewed. Beneath the ice lies an ocean of liquid water, kept warm by tidal heating, similar to Io though less extreme. This ocean is global, surrounding the entire moon, and it contains more water than all of Earth's oceans combined, perhaps twice as much. The ice shell is estimated to be 10 to 15 miles thick in most places, though there may be thinner regions where the ocean comes closer to the surface. Heat from tidal flexing warms the interior, and the rocky core might have hydrothermal vents on the ocean floor, similar to the vents on Earth's ocean floor, where superheated water rich in minerals erupts from cracks in the crust. On Earth, entire ecosystems thrive around these vents, independent of sunlight, powered by chemosynthesis. Bacteria convert chemicals from the vents into energy, and larger organisms feed on the bacteria. If Europa has similar vents, it could have life, organisms adapted to the darkness, thriving in the hidden ocean. Plumes of water vapor have been detected erupting from Europa's surface, geysers that shoot water hundreds of miles into space before it falls back as snow or escapes the moon entirely. These plumes offer a tantalizing possibility. A spacecraft could fly through the plumes and sample the ocean without even needing to land or drill through the ice. Analyzing the water could reveal whether organic molecules exist, whether the chemistry is right for life, maybe even detect life directly if any organisms get carried up in the plumes. Ganymede is the largest moon in the solar system, bigger even than the planet Mercury, though less massive because it contains a large amount of water ice. Ganymede is the only moon known to have its own magnetic field, likely generated by a liquid iron core. It also probably has a subsurface ocean, though deeper and less accessible than Europa's. Callisto, the outermost Galilean moon, is heavily cratered, ancient, geologically dead, though it too might have a subsurface ocean deep below its battered surface. Jupiter also has a ring system, though nothing like Saturn's spectacular rings. Jupiter's rings are faint, made of dust rather than ice, dark and difficult to see. They were discovered by Voyager 1 in 1979, a surprise find. The rings are constantly being replenished by dust kicked up when micrometeorites strike Jupiter's small inner moons. The dust spreads out into rings but gradually spirals into Jupiter or is blown away by the solar wind, so the rings only persist because new dust is constantly added. Jupiter's gravity shapes the entire outer solar system. Its immense mass affects the orbits of asteroids, creating gaps in the asteroid belt called Kirkwood gaps, where gravitational resonances with Jupiter prevent asteroids from maintaining stable orbits. Jupiter also acts as a cosmic shield for the inner solar system. Its gravity attracts comets and asteroids that would otherwise potentially strike Earth. In July 1994, humanity watched in real time as comet Shoemaker-Levy 9 broke into at least 21 fragments and crashed into Jupiter over the course of 6 days. Each impact released energy equivalent to millions of nuclear bombs, creating dark scars in Jupiter's clouds visible from Earth. Some of the impact sites were larger than Earth itself. The scars persisted for months before Jupiter's winds dispersed them. Without Jupiter, Earth would be hit by comets and asteroids far more frequently. Some scientists estimate that Jupiter reduces the impact rate on Earth by a factor of 1,000 or more. The history of life on Earth might have been very different without Jupiter's protection. More frequent catastrophic impacts could have prevented complex life from ever evolving, resetting the biosphere every few million years. Jupiter, just by existing in its orbit, has played a guardian role for the inner planets. Jupiter is sometimes called a failed star, and there is truth to that description. It is made of the same elements as the Sun, mostly hydrogen and helium. If Jupiter had been about 80 times more massive, about 13 times the mass of Jupiter that exists, the pressure and temperature in its core would have been high enough to ignite nuclear fusion, the process that powers stars. Hydrogen atoms would fuse into helium, releasing enormous energy, and Jupiter would have become a star. Our solar system would have been a binary star system, two stars orbiting each other with planets orbiting both. But Jupiter fell short. It gathered a tremendous amount of mass during the solar system's formation, but not quite enough to cross the fusion threshold. It remains a planet, albeit a planet so massive it blurs the line between planet and star. Brown dwarfs, objects larger than Jupiter but smaller than stars, do generate some heat through deuterium fusion, but Jupiter is not even massive enough for that. It is simply a very large ball of gas, slowly cooling, radiating away the heat from its formation, glowing faintly in infrared from internal warmth, but not generating new energy through fusion. Yet Jupiter still exerts star-like influence on its neighborhood. The four Galilean moons orbit Jupiter in a configuration reminiscent of planets orbiting a star, their orbits governed by the same physics of gravity and motion. Studying the Jupiter system taught us about how solar systems form and evolve. When we discover exoplanets around other stars, many of them are hot Jupiters, gas giants orbiting extremely close to their stars, nothing like our Jupiter. Understanding Jupiter helps us understand why our solar system has the architecture it does, with gas giants in the outer system and rocky planets in the inner system. Jupiter teaches about power that endures across billions of years, about storms that rage longer than civilizations exist, about magnetic fields that span millions of miles and trap radiation in belts of destruction, about moons that are worlds with oceans and volcanoes and mysteries we are only beginning to explore. Jupiter is ancient, patient, immense beyond human comprehension, a reminder that the universe operates on scales where planets are children's toys and time is measured in billions of years. We leave Jupiter in its court of attendant moons, traveling farther from the sun, deeper into cold and darkness. Ahead lies the next giant, one that wears the most beautiful crown in the solar system. Saturn waits, surrounded by rings of ice that catch and reflect sunlight, turning the planet into a jewel floating in the void. If you could visit only one place in the solar system with your own eyes, if you could choose a single sight to witness before you die, Saturn would reward you beyond any dream. The sixth planet from Sun, second largest, less massive than Jupiter but more spread out. A gas giant wrapped in subtle golden clouds and crowned with rings so magnificent that every person who sees Saturn through a telescope for the first time gasps. The rings make Saturn unmistakable, instantly recognizable, the most visually stunning object in our solar system. Saturn is named after the Roman god of agriculture, in time father of Jupiter, in mythology, and there is something timeless about Saturn, something serene and stately in the way it glides through space, with its rings tilted at angles that change as it orbits, sometimes showing us their full breadth, sometimes edge on when they nearly disappear. The planet itself is beautiful, even without the rings. Bands of clouds circle the equator in shades of gold and cream and tan, more subtle than Jupiter's vivid colors, but elegant in their restraint. Ammonia ice crystals, high in Saturn's atmosphere, catch sunlight and scatter it, giving the whole planet a soft golden glow. Storms appear occasionally as white spots against the golden backdrop, some persisting for months before dissipating. Saturn spins rapidly like Jupiter, completing a rotation in about 10 hours and 34 minutes, and this fast rotation creates jet streams that organize the clouds into bands and drive winds that can exceed 1,100 miles per hour at the equator, faster than the speed of sound. But the rings are what make Saturn transcendent. They are the most extensive ring system in the solar system. Nothing else remotely compares. Made of countless particles of water ice, each particle a tiny moon in its own right, ranging from dust grains to chunks the size of mountains. They reflect sunlight brilliantly because ice is so reflective, making Saturn appear brighter in our sky than it would without the rings. The rings extend outward from Saturn for 175,000 miles, nearly the distance from Earth to our moon, yet they are astonishingly thin, only about 30 feet thick in most places. If you scaled the rings down to the thickness of paper, they would be miles across. At their true scale, they are one of the thinnest structures relative to their diameter that exists anywhere. The rings are organized into distinct groups, separated by gaps. The main rings visible from Earth are labeled A, B, and C, with the B ring being the brightest and most massive. The Cassini division is a prominent gap between the A and B rings, discovered by astronomer Giovanni Cassini in 1675 using primitive telescopes, proof that even with crude instruments, the structure of the rings hints at complexity. Beyond the main rings are fainter rings labeled D, E, F, and G, some made of dust so fine they are only visible when backlit by the sun. The gaps in the rings are created by gravitational resonances with Saturn's moons. When ring particles orbit at certain distances, their orbital period becomes a simple ratio of a moon's orbital period, like 1/2 or 1/3. The repeated gravitational tugs from the moon at these resonances pull ring particles out of those orbits, clearing gaps. The Cassini division is maintained by the moon Mimas, whose orbital period is exactly twice that of particles in the division. Every two orbits, Mimas tugs on the same particles, gradually nudging them into different orbits, keeping the gap clear. Some moons, called shepherd moons, orbit within or near the rings and actively confine ring material through their gravity. Prometheus and Pandora shepherd the Pfeff ring, two small moons orbiting just inside and outside the narrow F ring, their gravity keeping the ring particles from spreading out. The F ring is chaotic, constantly changing, with kinks and braids, and clumps that appear and disappear over weeks or months, sculpted by the shepherds and by moonlets embedded within the ring itself. Where did the rings come from? Scientists are not entirely certain. One possibility is that they are the remnants of a moon that wandered too close to Saturn and was torn apart by tidal forces. Another possibility is that they formed from material left over from Saturn's formation that never coalesced into a moon. But here is the surprising part. The rings are young, geologically young. Analysis of data from the Cassini spacecraft suggests the rings may be only a few 100 million years old, perhaps less. This is puzzling because Saturn itself is 4.5 billion years old. Why would such spectacular rings form so recently in the planet's history? The rings are not stable over long timescales. They are constantly being eroded by meteoroid impacts that vaporize ice particles. They are being darkened by infalling dust and organic material from micrometeorites. They are slowly raining down onto Saturn, a gentle snow of ice particles falling into the planet's upper atmosphere. Cassini discovered that between 900 and 9,000 pounds of ring material falls into Saturn every second. At that rate, the rings are losing mass and will eventually disappear, though the timescale is uncertain, anywhere from 100 million to 300 million years from now. So the rings we see today might be relatively new, formed when a comet or moon broke apart near Saturn within the last few 100 million years. We are living in a special time when Saturn has rings. In the distant past, Saturn might have been ringless. In the future, the rings will be gone, and Saturn will be just another gas giant, still beautiful but no longer extraordinary. We exist in the brief window when Saturn wears its crown. At Saturn's North Pole, something bizarre exists that defies easy explanation. A hexagonal storm, a perfect geometric shape with 6 straight sides meeting at sharp angles, each side wider than Earth's diameter. This is not an optical illusion or a trick of image processing. It is a real atmospheric feature, a jet stream that flows in a hexagonal pattern. The hexagon was first discovered by Voyager spacecraft in 1980, then confirmed decades later by Cassini, which watched it for years. How does nature create a perfect hexagon? On Earth, storms are circular, following the rotation of the planet. But on Saturn, the combination of multiple jet streams at different latitudes, while moving at different speeds, interacts in a way that creates straight edges instead of curves. Scientists have recreated hexagonal patterns in laboratory experiments using rotating fluids at different speeds in concentric cylinders. When the speed difference is just right, the boundary between the fluids forms polygons, squares, or hexagons, depending on the parameters. Saturn's atmosphere is doing this naturally on a planetary scale, physics following mathematical rules that produce geometry. The hexagon rotates with the planet every 10 hours and 34 minutes, maintaining its shape year after year. Inside the hexagon is a central storm at the pole, a vortex with an eye like a hurricane. The whole structure is mesmerizing to watch in time lapse videos, the hexagon rotating steadily while clouds swirl within it. It is one of the most alien features in the solar system, a reminder that nature can create patterns that look designed but emerge purely from physical laws. Saturn is the least dense planet in the solar system. Its density is less than water, about 0.687 grams per cubic centimeter, compared to water's 1 gram per cubic centimeter. If you could find an ocean large enough, Saturn would float. This low density comes from its composition, mostly hydrogen and helium, spread over an enormous volume. Fast rotation causes Saturn to bulge even more dramatically than Jupiter, with the equatorial diameter about 10% larger than the polar diameter. Saturn looks noticeably oblate even in photographs, squashed by its own spin. Saturn has at least 146 confirmed moons, more than any other planet, though the count keeps increasing as astronomers discover tiny moonlets hiding in the rings or in distant orbits. Many of these moons are small, irregular chunks of rock and ice, probably captured asteroids or fragments from past collisions. But a few are large, substantial worlds in their own right, and two of them, Titan and Enceladus, are among the most interesting places in the entire solar system. Titan is the second largest moon in the solar system after Jupiter's Ganymede, and it is the only moon with a substantial atmosphere, thicker than Earth's atmosphere, in fact. When you look at Titan, you cannot see the surface at all. A thick orange haze surrounds the moon, hydrocarbon smog produced by sunlight, breaking apart methane in the upper atmosphere. This smog gives Titan a featureless orange appearance from space, hiding everything below. But radar can penetrate the haze, and what it reveals is astonishing. Titan has lakes and seas of liquid methane and ethane on its surface, the only other place in the solar system besides Earth with stable liquids on the surface. These are not small puddles. Kraken Mare, the largest sea, is bigger than the Caspian Sea on Earth, covering about 154,000 square miles. The seas are concentrated near the North Pole, while the South has smaller lakes. The liquids are hydrocarbons, natural gas in liquid form, kept liquid by the extreme cold, about minus 290 degrees Fahrenheit. Titan has a methane cycle analogous to Earth's water cycle. Methane evaporates from the seas, forms clouds in the atmosphere, and rains back down, carving river channels and filling lakes. Seasonal changes cause liquid to migrate between hemispheres. The Huygens probe, which landed on Titan in 2005, transmitted images and data from the surface showing rounded rocks made of water ice, shaped by flowing liquid, sitting in orange soil of hydrocarbon compounds. The sky above was orange, the air thick, the pressure at the surface about 50% higher than Earth's. Titan's atmosphere is mostly nitrogen, about 95%, with a few percent methane and traces of hydrogen and other gases. This nitrogen atmosphere is a mystery because nitrogen is too light to be held by Titan's weak gravity over geological time. It should have been lost to space billions of years ago, yet it persists, which means it is being replenished somehow, probably from ammonia in Titan's interior being broken down into nitrogen. Titan might have a subsurface ocean of liquid water mixed with ammonia beneath its icy crust, kept liquid by radioactive heating and pressure. The organic chemistry happening on Titan is incredibly complex. Tholins, large organic molecules, form in the atmosphere and rain down onto the surface, covering everything in a coating of organic gunk. These are prebiotic molecules, the kind of compounds that existed on Earth before life began. Titan is like a laboratory showing us what Earth might have been like billions of years ago, frozen in time at a stage before life emerged. Studying Titan helps us understand the chemistry that led to life on Earth. Enceladus is much smaller than Titan, only 313 miles in diameter, tiny enough to fit inside the state of Texas. But what it lacks in size, it makes up for in activity. Enceladus has the most reflective surface of any object in the solar system. White ice, so clean and pure, it reflects nearly 100% of sunlight that hits it. The surface is crisscrossed with fractures, and near the South Pole, something extraordinary happens. Geysers erupt from four parallel fractures called tiger stripes, shooting plumes of water vapor and ice particles over 300 miles into space. The plumes contain water, salt, silica, and organic molecules. The Cassini spacecraft flew through these plumes multiple times, sampling their composition directly. The water is coming from a global ocean beneath Enceladus' icy shell, kept liquid by tidal heating from Saturn. The ocean is in contact with a rocky core, and hydrothermal vents on the seafloor release heat and minerals into the water, creating an environment similar to hydrothermal vents on Earth's ocean floor. On Earth, these vents support thriving ecosystems. Life at the vents does not depend on sunlight. Bacteria use chemicals from the vents for energy through chemosynthesis, and entire food webs exist in the darkness. Enceladus has all the ingredients for life as we know it: liquid water, energy from hydrothermal vents, organic molecules, the right chemistry. If life can exist anywhere beyond Earth in our solar system, Enceladus is a top candidate. The notes from the geysers does not all fall back onto Enceladus. Some escapes the moon's weak gravity and spreads out along Enceladus's orbit, forming Saturn's A ring, a faint torus of tiny ice particles that extends from inside the orbit of Mimas out past the orbit of Dione. The A ring is being continuously replenished by Enceladus's geysers. Without that source, the ring would disappear in a few thousand years. Saturn takes 29.4 Earth years to complete one orbit around the Sun. Seasons last over 7 years each. From Earth, we see the rings change angle as Saturn moves through its orbit. When Saturn's equator is tilted toward us, the rings appear wide open, reflecting maximum light. As Saturn continues its orbit, the tilt changes and the rings appear to close, narrowing until they are edge on. When the rings are edge on, they nearly disappear from view even through telescopes because they are so thin. For a few weeks, Saturn appears ringless, a golden ball in space. Then the rings open again as Saturn continues its path, gradually widening until they reach maximum tilt the other way. This cycle repeats every 29 years, and astronomers have been watching it for centuries. The Cassini spacecraft spent 13 years orbiting Saturn from 2004 to 2017, revolutionizing our understanding of the planet and its moons. Cassini discovered new moons, watched storms develop and dissipate, flew through Enceladus's geysers, dropped the Huygens probe onto Titan, studied the rings in unprecedented detail. When Cassini finally ran low on fuel, Mission controllers commanded it to dive into Saturn's atmosphere to avoid any possibility of crashing into and contaminating Enceladus or Titan with Earth microbes. On September 15, 2017, Cassini plunged into Saturn, transmitting data until the very end, then burned up in the atmosphere, becoming part of the planet it had studied for so long. It was a fitting end for a mission that revealed so much beauty. Saturn teaches that beauty exists even in the cold outer solar system, far from the sun's warmth, that nature can create wonders like rings and hexagons through nothing but gravity and fluid dynamics, that moons can be as interesting as planets, hiding oceans and geysers and lakes of methane. Saturn is grace and elegance, a planet that invites contemplation, that rewards anyone who looks at it through a telescope with a sight they will never forget. We leave Saturn with reluctance, its rings growing smaller behind us, and travel deeper into the cold. The next planet is strange beyond even Saturn's wonders. Uranus awaits, knocked onto its side by ancient violence, rolling through space like a ball, blue and silent and utterly unlike anything closer to the Sun. Seventh planet from Sun, and the first planet discovered with a telescope, expanding humanity's known solar system beyond the 5 planets visible to naked eye. William Herschel found it in 1781 while systematically surveying stars, noticing one that appeared as a disk rather than a point of light and moved against the background stars. At first, he thought it was a comet, but calculations showed it was orbiting far beyond Saturn in a nearly circular orbit. It was another planet, a world that had been there all along, invisible to the ancients, waiting to be noticed. Herschel wanted to name it Georgium Sidus, George's star, after King George III of England. Fortunately, that name did not stick. Other astronomers suggested Herschel, naming it after its discoverer, but eventually the tradition of using mythological names prevailed. Uranus, the Greek god of the sky, grandfather of Jupiter, seemed fitting. It is the only planet named after a Greek rather than Roman god, a small break in the pattern. Uranus is not a gas giant like Jupiter and Saturn. It is an ice giant, a fundamentally different kind of world. Instead of being mostly hydrogen and helium, Uranus is made primarily of water, methane, and ammonia ices, though the term ices is misleading because at the temperatures and pressures inside Uranus, these materials are not frozen solid. They exist in hot, dense forms, compressed until they behave more like fluids than either ice or gas. The interior of Uranus is probably an ocean of these materials, thousands of miles deep, surrounding a rocky core. Something catastrophic happened to Uranus early in its history. The planet rotates on its side, tilted 98 degrees relative to its orbital plane. Most planets spin roughly upright, with their axes tilted only slightly. Earth's axis is tilted 23.5 degrees, giving us moderate seasons. Jupiter's axis is tilted only 3 degrees, barely at all. But Uranus's axis is nearly parallel to its orbital plane. The planet does not spin like a top, it rolls like a ball. This extreme tilt means that during Uranus's 84-year orbit around the Sun, each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. Imagine a day-night cycle measured in decades. For 42 years, the North Pole faces the Sun directly, bathed in constant light, while the South Pole is plunged into endless night. Then Uranus moves to the opposite side of its orbit, and the situation reverses. The South Pole gets 42 years of sunlight, while the North Pole freezes in darkness. The equator experiences more normal day night cycles, but the sun appears to circle the horizon rather than rise and set in the east and west. What caused this bizarre tilt? The most likely explanation is a massive collision early in the solar system's history. A protoplanet, perhaps the size of Earth, struck Uranus with such force that it knocked the entire planet onto its side. The impact would have been cataclysmic, vaporizing both the impactor and part of Uranus, releasing energy that briefly made the collision site hotter than the sun. Debris from the impact might have formed Uranus's moons, or the moons might have been knocked over along with the planet. Either way, Uranus was fundamentally changed by violence, and it has never recovered. Uranus is the coldest planetary atmosphere in the solar system, even colder than Neptune, which is farther from the Sun. Temperatures in Uranus's upper atmosphere drop to minus 371 degrees Fahrenheit, just 70 degrees above absolute zero, the coldest anything can possibly be. This is strange because Uranus should be warmer than Neptune based on distance from the Sun. Neptune is 900 million miles farther out and receives much less sunlight, but Neptune is warmer because it radiates more internal heat than Uranus. For reasons scientists still debate, Uranus releases very little heat from its interior. Jupiter, Saturn, and Neptune all radiate roughly twice as much energy as they receive from the Sun, still glowing from the heat of their formation or from ongoing gravitational contraction. But Uranus radiates almost exactly the same amount of energy it receives, no internal heat source contributing to its warmth. Perhaps the collision that knocked it sideways also disrupted its internal heat flow, causing the interior to become stratified with heat trapped deep inside, unable to reach the surface, or perhaps Uranus simply lost its internal heat faster than the other giants. Whatever the reason, Uranus is a cold, quiet world, almost inert compared to the violent activity on the other gas and ice giants. The blue-green color of Uranus comes from methane in its atmosphere. Methane molecules absorb red wavelengths of light and reflect blue and green wavelengths back into space. The atmosphere is about 83% hydrogen, 15% helium, and 2% methane, with traces of water, ammonia, and other compounds. From Earth, Uranus appears as a pale blue-green dot, serene and featureless. When Voyager 2 flew past in January 1986, the only spacecraft ever to visit Uranus, it saw a disappointingly bland planet, just a smooth blue sphere with almost no visible cloud features. Scientists thought Uranus was a dead world, geologically and meteorologically inactive, its tilted axis and lack of internal heat creating a calm, stable atmosphere. But they were wrong about the timing. Voyager arrived during Uranus's equinox, the brief period every 42 years when neither pole faces the sun directly and the entire planet experiences something closer to normal seasonal conditions. The atmosphere was in a transitional state, not showing its full range of activity. Decades later, as Uranus moved through its orbit and one pole began tilting toward the sun again, telescopes on Earth saw the planet come alive. Bright clouds appeared, massive storms developed in the atmosphere, wind speeds increased, the bland blue ball transformed into an active, dynamic world. Infrared observations revealed storms larger than Earth churning in Uranus's atmosphere, rising from deep layers and becoming visible as bright spots against the blue background. These storms form and dissipate over weeks or months, driven by heating as one hemisphere emerges from decades of darkness into sunlight. The extreme seasons create weather patterns unlike anywhere else, delayed responses to heating that take years to manifest, atmospheric waves propagating around the planet. Uranus has 13 known rings, much darker than Saturn's brilliant ice rings, made of dark particles, possibly organic compounds baked by radiation. The rings are narrow and difficult to see. They were discovered in 1977 when Uranus passed in front of a distant star as seen from Earth. Astronomers were watching to study Uranus's atmosphere by how it dimmed the starlight, but before the planet itself blocked the star blinked on and off several times. After Uranus passed, the star blinked again in a symmetrical pattern. Something was orbiting Uranus and blocking the starlight. Rings. 9 rings were discovered that night, and later observations found 4 more. The rings are composed of dark material that reflects only a few percent of sunlight, the opposite of Saturn's bright ice rings. The particles might be darkened by radiation or coated in organic compounds. The rings are confined to narrow bands, kept in place by shepherd moons, whose gravity prevents the particles from spreading. The rings follow Uranus's tilted equator, orbiting perpendicular to the plane of Uranus's orbit around the Sun, another consequence of the planet's extreme axial tilt. Uranus has 28 known moons, all of them orbiting in the plane of the tilted equator, suggesting they formed after the collision that tipped the planet over or were captured and had their orbits altered. The moons are named after characters from the works of William Shakespeare and Alexander Pope, breaking the tradition of naming moons after mythological figures. Miranda, Ariel, Umbriel, Titania, and Oberon are the 5 largest, each one a frozen world with its own character. Miranda is the most bizarre moon in the solar system. Its surface looks like it was assembled from mismatched pieces, a chaotic jumble of different terrains that make no geological sense. Massive cliffs called Verona Roops rise up to 12 miles high, the tallest known cliff in the solar system. If you jumped off the top on Miranda's weak gravity, it would take about 10 minutes to fall to the bottom. Grooved terrain covers parts of the surface, parallel ridges and valleys etched into the ice. Ancient cratered plains sit next to younger, smoother regions. The whole moon looks broken. One theory suggests Miranda was shattered by a catastrophic impact that broke it into pieces. Gravity pulled the fragments back together, but they reassembled in the wrong order, creating the chaotic surface we see today. Another theory proposes that tidal heating from Uranus partially melted Miranda's interior, causing ice to rise and create the grooved terrain, but then the heating stopped and the surface froze in its partially reshaped state. Whatever happened, Miranda is a world that experienced violence and never fully recovered, frozen in a moment of geological trauma. Uranus's magnetic field is one of the strangest in the solar system. On Earth and most other planets, the magnetic field roughly aligns with the rotation axis, with magnetic field lines emerging from near the poles. But Uranus's magnetic field is tilted 59 degrees away from its rotation axis and offset from the center of the planet by about 1/3 of the radius. As Uranus rotates, the magnetic field wobbles wildly, creating a corkscrew pattern in space. The magnetic poles are not where the geographic poles are. One magnetic pole is closer to the equator than to the North Pole. This bizarre magnetic field probably originates not in the core, but in the mantle, the deep layer of water, methane, and ammonia ices. Under the extreme pressure and temperature in this region, these materials become electrically conductive, able to carry currents that generate magnetic fields. The flow patterns in this mantle layer must be complex and asymmetric, producing a magnetic field that does not align with the planet's rotation. Neptune has a similarly tilted and offset magnetic field, suggesting both ice giants generate their fields in their mantles rather than in their cores. The tilted magnetic field creates auroras on Uranus, but not at the poles like on Earth. Instead, auroras appear at various latitudes, wherever the magnetic field lines happen to intersect the atmosphere. As Uranus rotates, the auroras move around the planet, appearing and disappearing in different locations. Observers on Uranus would see auroras in strange places, not confined to polar regions, a visual reminder that the planet's magnetic geography is as broken as its axial tilt. Uranus takes 84 Earth years to orbit the Sun, moving so slowly across the sky that ancient people never noticed it was a planet. It completed its first observed orbit in 1865, 84 years after its discovery. Anyone born the year Uranus was discovered would have died before seeing it return to the same position. The planet moves with stately patience, one season lasting 21 years, giving time for atmospheric changes to develop slowly, heat and cold accumulating over decades. Scientists are still debating exactly how Uranus and Neptune formed. They are different from Jupiter and Saturn, smaller, icier, with different compositions. Perhaps they formed closer to the Sun, where ice was more abundant, then migrated outward to their current orbits. Perhaps they formed where they are now, in the cold outer reaches, but did not have enough time to gather as much hydrogen and helium as Jupiter and Saturn before the solar nebula dissipated. Computer simulations suggest that the outer solar system was chaotic during the formation period, with giant planets migrating, swapping positions, scattering smaller bodies. Uranus and Neptune might have formed closer together and then been pushed apart by gravitational interactions. The truth remains uncertain, another mystery Uranus keeps. There is something quietly tragic about Uranus, a world that was knocked sideways by violence so extreme it changed the fundamental nature of the planet. Uranus spins on its side, rolls through space instead of spinning upright, experiences seasons no other planet knows. Its magnetic field is broken, offset and tilted, creating a magnetosphere that changes shape every rotation. Its internal heat flow was disrupted, leaving it colder than it should be. Uranus was profoundly damaged early in its history, and the scars remain visible billions of years later. Yet it endures. It holds its moons, maintains its rings, orbits the sun in a stable path. Uranus has been spinning on its side for 4.5 billion years, and it will continue for billions more. There is resilience in that. Survival despite catastrophe, continuing to exist even after being fundamentally broken. Uranus teaches that worlds can suffer violence beyond imagination and still persist, still follow their paths, still be part of the cosmic dance. We leave the tilted world behind and journey to the last planet, the farthest from the sun still counted among the eight. Neptune waits in the deep blue distance, a world discovered not by seeing it first, but by mathematics, a triumph of human intellect predicting what should exist based on gravitational perturbations, then looking and finding it exactly where the equations said it should be. Neptune is windswept and active despite the cold and distance, a reminder that even at the edge of the planetary realm, worlds can be alive with energy and mystery. Eighth planet from Sun, the last true planet in our solar system, and the only planet discovered through mathematical prediction before it was observed. In the early 1840s, astronomers noticed that Uranus was not moving quite right. Its orbit deviated slightly from the predictions made by Newton's laws of gravity. Something massive beyond Uranus was pulling on it, perturbing its path. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this unknown planet must be located based on the anomalies in Uranus's orbit. Le Verrier sent his predictions to Johann Galle at the Berlin Observatory, and on the night of September 23rd, 1846, within hours of beginning the search, Galle found Neptune less than 1 degree from the predicted position. It was a triumph of physics and mathematics, proof that the laws of gravity could predict the existence of worlds that had never been seen. Humans found Neptune not by looking for it, but by reasoning that it must exist and calculating its location. Named after the Roman god of the sea for its deep blue color, Neptune validated humanity's understanding of celestial mechanics and showed that the solar system held more than met the eye. Neptune is blue, but not like Uranus's pale blue-green. Neptune's blue is richer, deeper, more saturated, the color of the ocean at its darkest depths. Methane in the atmosphere absorbs red light, just like on Uranus, but Neptune's blue is more intense for reasons scientists still do not fully understand. There must be another component in Neptune's atmosphere, some molecule or compound that enhances the blue color beyond what methane alone can explain. Nobody has identified this mystery compound yet. Neptune keeps its secrets. Neptune holds the record for the fastest winds in the entire solar system, and this should not be possible. Wind speeds on Neptune reach 1,200 miles per hour, supersonic speeds that would tear apart anything in their path. On Earth, our fastest winds, inside the most powerful tornadoes and hurricanes, barely exceed 300 miles per hour. Neptune's winds are 4 times faster, and they blow constantly, jet streams racing around the planet at speeds that exceed the speed of sound in Neptune's atmosphere. This is deeply strange because wind is driven by heat, by temperature differences, creating pressure gradients that cause air to flow from high pressure to low pressure. On Earth, the sun provides the energy that creates our weather. Heating at the equator and cooling at the poles creates the temperature differences that drive winds and ocean currents. But Neptune is 30 times farther from the sun than Earth, 2.8 billion miles away. It receives only 1/900th as much sunlight as Earth, barely any solar energy at all. There should not be enough energy to power violent weather. Yet, the winds rage. The answer lies within Neptune itself. Like Jupiter, Saturn, and unlike Uranus, Neptune radiates more than twice the energy it receives from the sun. Internal heat drives the storms, energy slowly leaking out from the planet's formation 4.5 billion years ago. But where is the heat coming from? Gravitational contraction, as the planet very slowly shrinks, could generate some heat. Chemical reactions deep in the atmosphere might contribute. One fascinating theory suggests it rains diamonds inside Neptune. Methane in Neptune's atmosphere is broken apart by heat and pressure deep below the visible clouds. The carbon atoms freed from methane bond together under immense pressure, forming diamonds. These diamonds, possibly the size of raindrops or even larger, fall toward the core like hail, sinking through the dense layers of Neptune's interior. As they fall, gravitational potential energy converts to heat, warming the interior. Eventually, the diamonds might reach depths where the pressure and temperature are so extreme they melt into liquid carbon or even dissolve back into the surrounding material. Experiments on Earth using powerful lasers to recreate the conditions inside ice giants have shown that diamond formation is possible, even likely. Neptune might have an ocean of liquid carbon deep in its interior, with diamond icebergs floating in it, a treasure beyond imagining hidden forever beneath the clouds. When Voyager 2 reached Neptune in August 1989, the last stop on its grand tour of the outer solar system, it discovered a massive storm in Neptune's southern hemisphere, the Great Dark Spot. Similar in structure to Jupiter's Great Red Spot, was an anticyclonic storm about the size of Earth, with winds screaming around its edges. Bright white clouds accompanied the spot, methane ice crystals condensing at high altitude as gas was forced upward by the storm's circulation. But unlike Jupiter's Great Red Spot, which has lasted for centuries, Neptune's Great Dark Spot was temporary. When the Hubble Space Telescope turned its gaze to Neptune in 1994, the Great Dark Spot was gone, vanished completely. But new storms had appeared in other locations. Neptune's atmosphere is constantly changing, storms forming and dissipating on timescales of months or years, driven by the internal heat and the complex interactions between different layers of the atmosphere. One storm, nicknamed the Scooter, moved faster than the Great Dark Spot, overtaking it during Voyager's observation period, proof that different atmospheric layers move at different speeds. Neptune takes 165 Earth years to orbit the Sun, an orbit so vast and slow that since its discovery in 1846, it did not complete one full orbit until 2011. Every season lasts more than 40 years. Right now, Neptune is in southern spring, which will last until 2046. But something strange happens with Neptune's temperature. The southern hemisphere has been emerging from winter and should be warming as it receives more sunlight. Instead, observations show that Neptune has been cooling slightly over the past 2 decades. Nobody knows why. Perhaps the atmospheric circulation has changed, redistributing heat in unexpected ways. Perhaps the internal heat output varies over time. Neptune's climate is influenced more by internal heat than by the sun, creating weather patterns that do not follow simple seasonal predictions. Despite being the farthest planet from the sun, Neptune is the warmest of the ice giants. Its core temperature is estimated at about 9,000 degrees Fahrenheit, surrounded by a mantle of water, methane, and ammonia in hot, dense phases that do not exist naturally on Earth. Under millions of atmospheres of pressure, these materials are compressed into exotic states, supersonic water, where oxygen atoms form a lattice and hydrogen atoms flow through it like a liquid, conducting electricity and generating Neptune's magnetic field. The heat from the core conducts slowly outward, powering the weather, creating the winds and storms that make Neptune the most dynamic of the outer planets. Neptune has 16 known moons, but one stands above all others in strangeness. Triton, the largest moon, is the only large moon in the solar system with a retrograde orbit, orbiting in the opposite direction to Neptune's rotation. This immediately tells us that Triton did not form where it is. It was captured, pulled from somewhere else by Neptune's gravity, and forced into orbit. Most likely, Triton originated in the Kuiper Belt, the region of icy objects beyond Neptune's orbit, and wandered too close to the planet billions of years ago. Neptune's gravity captured it, but the capture was violent, forcing Triton into a highly elliptical and inclined orbit. Tidal forces from Neptune gradually circularize the orbit over millions of years, but the retrograde direction remains, proof of Triton's foreign origin. Triton's surface is the coldest measured anywhere in the solar system, minus 391 degrees Fahrenheit, just 68 degrees above absolute zero. At these temperatures, nitrogen freezes solid. Triton's surface is made of nitrogen ice mixed with frozen methane and water ice, creating a landscape of pink and white terrains. The South Polar region is covered by a bright cap of frozen nitrogen and methane that sublimates in summer and refreezes in winter, changing the appearance of the moon over Triton's seasons. But Triton is not geologically dead, despite the extreme cold. Geysers erupt from its surface, plumes of nitrogen gas, and dark organic particles shooting 5 miles into space. The Voyager 2 spacecraft observed active geysers during its flyby, a surprise that nobody expected. The geysers are probably driven by solar heating, weak as it is. Sunlight penetrates the translucent nitrogen ice, warming darker material beneath. The heat vaporizes nitrogen, and pressure builds until it breaks through the ice, erupting like a geyser. The gas carries dark particles with it, and these particles fall back to the surface downwind of the vent, creating dark streaks visible in images of Triton. Triton might also have a subsurface ocean, kept liquid by tidal heating and radioactive decay. If so, it would be another potential habitat for life, though the conditions are far more extreme than Europa or Enceladus. Triton is one of the most geologically diverse moons, with cantaloupe terrain, wrinkled regions that look like the skin of a melon, smooth volcanic plains where water ice lava once flowed, few impact craters, indicating a young surface constantly renewed. But Triton is doomed. Its retrograde orbit is slowly decaying. Tidal forces between Neptune and Triton are stealing energy from Triton's orbit, causing the moon to spiral inward at about 1.5 inches per year, a tiny amount but relentless. In about 3.6 billion years, Triton will reach the Roche limit, the distance at which Neptune's tidal forces will overcome Triton's own gravity. The moon will break apart, torn into fragments by tidal stress. Those fragments will spread out into a ring around Neptune, creating a ring system that might rival Saturn's in beauty and extent, or Triton might crash into Neptune before reaching the Roche limit, a collision between moon and planet, adding Triton's mass to Neptune in a brief flash of violence. Either way, Triton's time is limited. It is a captured object, forced into an unstable orbit, slowly counting down the millions of years until destruction. There is tragedy in that. A moon that survived for billions of years in the Kuiper Belt, untouched and independent, only to be captured and sentenced to eventual annihilation. Neptune has 5 main rings, dark and faint like Uranus's rings, but with unique features. The rings are made of dust and dark particles, possibly organic material darkened by radiation. The outermost ring, The atom's ring has bright clumps called ring arcs, concentrated regions where material has gathered. These arcs defy expectations because material in a ring should spread out evenly over time through collisions and orbital mechanics. Yet the arcs persist, kept in place by gravitational resonances with the small moon Galatea orbiting nearby. The arcs are named for the scientists involved in Neptune's discovery: Liberté, Égalité, Fraternité, and Courage. From Neptune, the sun is just a very bright star, not a disk but a point of light, 1,000 times dimmer than seen from Earth. There is no warmth from that distant light, no sense of being in a solar system at all. Neptune exists in cold darkness at the edge of the sun's influence, where the solar wind weakens and interstellar space begins to intrude. The solar system is vast beyond normal comprehension, and Neptune marks the boundary of the known planetary realm. Voyager 2 is the only spacecraft ever to visit Neptune. Its flyby in August 1989, the last planetary encounter of the Grand Tour. Voyager revealed a dynamic world, discovered 6 new moons, confirmed the rings, photographed Triton's geysers, measured Neptune's winds and magnetic field. The images sent back showed a vivid blue planet with white clouds, a world more active and interesting than anyone expected. After Neptune, Voyager 2 continued outward, now in interstellar space beyond the heliopause, still transmitting data over 40 years after launch, the farthest human-made object, along with Voyager 1. No missions are currently planned to return to Neptune. The distance is enormous. The journey takes over a decade with current technology, and funding for outer solar system missions is limited, but proposals exist for orbiters or flybys, missions that could study Neptune and Triton in detail, map the magnetic field, measure the internal heat output, search for subsurface oceans. Maybe in the next few decades, another spacecraft will make the journey, and we will see Neptune again through new instruments. Neptune teaches that distance from the Sun does not mean dead or inactive, that internal heat can drive complex weather even in the outer solar system's cold, that moons can be captured from elsewhere and forced into doomed orbits, that mathematics can predict reality, that human minds can find worlds by calculation before seeing them. Neptune was the last planet discovered in our solar system, unless a ninth planet exists far beyond, a hypothetical world inferred from orbital perturbations, but not yet found. Until then, Neptune marks the edge, the final stop among the 8, the wind chaser at the boundary between the known and the unknown. We have traveled from Mercury to Neptune now, visiting 8 worlds of fire and ice, stone and storm, beauty and violence. But the journey is not complete. Something still waits to be understood, a final truth that connects everything. The question we asked at the beginning remains: why do these planets exist at all? What invisible force binds them together? The answer lies not in any single planet, but in the story of how they all came to be and what they mean for us. The final section will reveal this truth, bringing the journey full circle, connecting you to the stars in a way you perhaps never expected. Our journey took us through 8 worlds, each one a chapter in a story written across billions of years. But the solar system does not end at Neptune. Beyond lies the Kuiper Belt, a vast region of icy objects stretching from Neptune's orbit out to about 50 astronomical units from the Sun, home to thousands of small worlds, comets waiting in the cold, and dwarf planets that challenge our definitions of what a planet should be. Pluto orbits here, the world that was once called the ninth planet, discovered in 1930 by Clyde Tombaugh, a young astronomer searching systematically through photographic plates, comparing images taken nights apart, looking for something that moved. He found Pluto, a tiny dot shifting position against the background stars, and for 76 years it held the title of planet. Children learned 9 planets in school. Pluto was the oddball, small and distant, with an elliptical orbit that sometimes brought it closer to the Sun than Neptune, but still counted among the family. Then in 2006, the International Astronomical Union reclassified Pluto as a dwarf planet, a decision that sparked controversy and emotional responses from people who had grown up with 9 planets. But the reclassification was not arbitrary. Astronomers had discovered other objects in the Kuiper Belt, similar in size to Pluto. Eris, found in 2005, is actually more massive than Pluto. Haumea and Mako orbit even farther out. If Pluto was a planet, then these others should be too, and the list would keep growing as more objects were discovered. The Kuiper Belt is populated with Pluto-sized worlds, so astronomers created a new category. Dwarf planets are objects massive enough that their own gravity pulls them into roughly spherical shapes, but not massive enough to clear their orbital neighborhoods of other debris. Pluto shares its orbital space with thousands of other Kuiper Belt objects. It has not gravitationally dominated its region the way that 8 planets have. Under the new definition, Pluto became the prototype for a class of dwarf planets, the first of many rather than the last of the old guard. But reclassifying Pluto does not diminish its wonder. In July 2015, the New Horizons spacecraft flew past Pluto after a 9.5-year journey across the solar system. What it revealed stunned everyone. Pluto was not a dead, frozen rock. Its surface showed a heart-shaped plain of frozen nitrogen called Sputnik Planitia, smooth and bright, possibly less than 10 million years old. Mountains of water ice rose 3 miles high, as hard as rock in the extreme cold. Blue atmospheric haze surrounded the planet, organic molecules created by sunlight breaking apart methane. Red organic compounds, tholins, covered parts of the surface like snow. Pluto might have a subsurface ocean of liquid water kept warm by radioactive decay in its rocky core. Geysers or cryovolcanoes might erupt water and ammonia onto the surface. Active geology on a world that should be frozen solid, 3.7 billion miles from the sun, where sunlight is 1,000 times weaker than on Earth. Pluto defied expectations, proving that even at the edge of the solar system, worlds surprise us. Worlds are more complex and beautiful than we imagine. Beyond the Kuiper Belt, perhaps a light year from the sun, lies the Oort cloud, a spherical shell of icy objects surrounding the entire solar system. The Oort cloud has never been directly observed. It is too far away, the objects too small and dark to see with current telescopes, but it must exist to explain the long-period comets that occasionally fall into the inner solar system from random directions, comets with orbits taking thousands or millions of years to complete. These comets come from the Oort cloud, nudged by gravitational perturbations from passing stars or the tidal forces of the galaxy itself, falling toward the sun from the outer edge of its gravitational influence. The Oort cloud marks the true boundary of the solar system, the region where the sun's gravity fades and interstellar space begins. It extends halfway to the nearest star, a distance so vast that light from the sun takes months to reach the outer Oort cloud. If you could stand there, the sun would be just another star, bright but not dominant, one light among many in the cold cosmic dark. We have seen the end of the planetary realm. Now we must return to the beginning to understand why any of this exists at all. 4.5 billion years ago, the solar system did not exist. In its place floated a cloud of gas and dust, a molecular cloud drifting through interstellar space. This cloud was made mostly of hydrogen and helium, the primordial elements created in the Big Bang, but it also contained heavier elements: carbon, oxygen, nitrogen, silicon, iron, all the elements necessary to build planets and life. These heavier elements were not created in the Big Bang. They were forged in the cores of massive stars that lived and died before the sun existed. Stars are nuclear furnaces. In their cores, hydrogen atoms fuse into helium, releasing energy that makes stars shine. As stars age, they fuse helium into carbon and oxygen, then into heavier elements, building up the periodic table through nuclear reactions. The most massive stars fuse elements all the way to iron, creating every element lighter than iron through fusion. When these massive stars exhaust their fuel, they explode as supernovae, blasting their enriched material into space. In the violence of the explosion, elements heavier than iron are created: gold and uranium and all the rest, forged in the inferno and scattered into the cosmos. The molecular cloud that became our solar system was made of material from previous generations of stars, stardust. Literally, the remnants of stars that had lived their lives and died, recycling their atoms back into the interstellar medium. The cloud drifted, mixing with other clouds, accumulating mass, growing denser. Then something triggered its collapse. Perhaps a nearby supernova explosion sent a shockwave through space, compressing the cloud. Perhaps the collision with another cloud provided the nudge. Whatever the cause, the cloud began to collapse under its own gravity. As it collapsed, it began to spin. Conservation of angular momentum, the same principle that makes a figure skater spin faster when pulling their arms in, caused the cloud to rotate faster as it contracted. The spinning cloud flattened into a disk, the protoplanetary disk, with a dense concentration at the center and material spread out in a thin plane around it. The center grew hotter and denser as more material fell into it, pressure and temperature increasing until nuclear fusion ignited. The sun was born. But the disk around the young sun still contained a tremendous amount of material, and this material would become the planets. In the inner solar system, close to the sun, temperatures were high, over 1000 degrees Fahrenheit in some regions. Only materials that could withstand this heat survived as solids. Metals like iron and nickel remained solid. Rocky materials, silicates, and oxides condensed from vapor into solid grains, but volatile materials, water, methane, ammonia, remained as gases too hot to freeze. These solid particles, grains of metal and rock, collided with each other as they orbited the young sun. When they collided gently, they stuck together, electrostatic forces and gravity holding them. Grain by grain, these particles grew into larger bodies called planetesimals, pebble-sized to mountain-sized objects scattered through the disk. Planetesimals collided with each other, sometimes shattering, sometimes merging. The larger ones had stronger gravity and attracted more material, growing faster through countless collisions over millions of years. Planetsimals merged into protoplanets, moon-sized or Mars-sized bodies. The final stage of planet formation was violent. Protoplanets collided with each other in giant impacts that released more energy than all of Earth's nuclear weapons combined. These collisions were common in the early solar system, the last stages of clearing the inner system of debris and assembling the final planets. Earth itself formed from dozens or hundreds of protoplanet collisions. The impact that formed the moon was just one of many, though it was among the last and largest. Mercury, Venus, Earth, and Mars formed from this process, rocky worlds with iron cores, built from materials that could survive the heat close to the sun. They are small because there was less material available in the inner solar system. Most of the disk's mass was hydrogen and helium, which could not condense into solids in the heat. Beyond the frost line, about 4 astronomical units from the sun, temperatures were cold enough for water ice to form. This changed everything. Ice is far more abundant than rock and metal in the universe because oxygen is common and readily bonds with hydrogen. Beyond the frost line, the solid material available included not just rock and metal, but also vast amounts of ice. Planetesimals grew larger faster because more material was available. Jupiter and Saturn formed massive cores of rock and ice, perhaps 10 to 20 Earth masses, large enough that their gravity became powerful enough to capture hydrogen and helium from the surrounding disk. Gas spiraled onto these cores, adding layer after layer of atmosphere, growing into gas giants wrapped in hydrogen thousands of miles deep. They became more like stars than planets in composition, mostly hydrogen and helium, but not massive enough to ignite fusion. Uranus and Neptune formed farther out where the disk was less dense. They gathered cores of rock and ice, but did not grow large enough, fast enough to capture significant amounts of hydrogen and helium before the solar wind from the young sun blew away the remaining gas in the disk. They became ice giants, smaller than Jupiter and Saturn, with thick mantles of water, methane, and ammonia, but relatively thin outer atmospheres. The architecture of the solar system, rocky planets close in and gas giants farther out, results directly from the temperature gradient in the protoplanetary disk. Heat from the forming sun determined what materials could condense at different distances, and this determined what kinds of planets formed. It is a natural sorting process driven by physics. But here is the invisible force that holds it all together, the answer to the question from the beginning: gravity. Gravity pulled the molecular cloud together, starting the collapse. Gravity concentrated material at the center, forming the sun. Gravity caused the disk to flatten and spin. Gravity pulled particles together into planetesimals. Gravity drove the collisions that built planets. Gravity holds the planets in their orbits, balancing the inward pull of the sun with the outward motion of their orbital velocities. Every planet orbits because it is falling toward the sun, but moving sideways fast enough that it keeps missing. Orbital motion is perpetual falling, curving around the sun in an ellipse or near circle, gravity constantly pulling inward while inertia carries the planet forward. This balance has been maintained for 4.5 billion years and will continue for billions more. Gravity is the architect, the sculptor, the force that shapes everything from galaxies down to planets, the fundamental interaction that makes structure possible in the universe. But there is a deeper truth waiting, the realization that changes everything once you truly understand it. You are made of the same material as the planets. Every atom in your body came from the protoplanetary disk that formed the solar system, or from earlier generations of stars before that. The iron in your blood was forged in a supernova explosion, created in the final moments of a massive star's life and scattered into space. The calcium in your bones formed in the core of a dying star through nuclear fusion. The carbon in every cell, the oxygen you breathe, the nitrogen in your DNA, all of it created in stellar furnaces and expelled into the cosmos when those stars died. You are not separate from the planets. You are made of planet material, stardust that coalesced on Earth instead of in space. The same physics that formed Mercury and Venus and Mars formed you. The same gravity that holds planets in orbit pulls on every atom in your body. The same nuclear forces that power the sun power the chemical reactions in your cells. You are a temporary pattern that matter has arranged itself into, but the matter itself is ancient, recycled through multiple generations of stars, billions of years old. When you look at planets, you are looking at family, distant cousins born from the same cloud of gas and dust, shaped by the same forces, following the same laws of physics. The loneliness of Mercury, the nightmare of Venus, the miracle of Earth, the loss of Mars, the grandeur of Jupiter, the beauty of Saturn, the resilience of Uranus, the winds of Neptune. These are not just stories about distant objects, they are chapters in your story because you came from the same place. 4.5 billion years ago, a cloud of stardust began to collapse. Most of it formed the sun. Some formed planets. A tiny fraction landed on Earth and eventually became you. The universe created the atoms. Stars forged them into complex elements. Gravity gathered them into planets. Chemistry organized them into life. And evolution shaped them into consciousness. You are the universe's way of experiencing itself, matter arranged into a pattern complex enough to ask questions about where it came from. Why do planets exist? The same reason you exist, because gravity shaped chaos into order, because the laws of physics allow structure to emerge from randomness, because matter organizes itself when conditions are right. Stars, planets, life, consciousness, all of it emerging from simple rules playing out over immense timescales. The planets are not just objects to study, they are part of the same process that created you, the same story written in atoms and gravity and time. Carl Sagan once described Earth as a pale blue dot, seen from the edge of the solar system by Voyager 1 as it looked back at the inner planets. In that image, Earth is tiny, a fraction of a pixel, barely visible against the vastness. Every human who ever lived existed on that dot. Every civilization, every war, every love story, every discovery, all of it confined to one small world spinning in darkness. Sagan used that image to illustrate both the insignificance and the preciousness of Earth, how small we are in cosmic scale, but how important we are to each other. But knowing our cosmic origins does not make us small, it makes us miraculous. We are the universe becoming aware of itself. Matter evolved to the point where it can contemplate its own existence, ask questions about meaning and purpose, create art and science, and love. We are made of stars, and we know we are made of stars, and that knowledge is itself extraordinary. Tonight you learned 100 facts about planets, but more than facts, you learned a story about connection, about origins, about the deep relationship between you and the cosmos. The planets spin in their orbits, following paths laid down billions of years ago, patient and eternal. Mercury still bakes and freezes in endless cycle. Venus still burns beneath acid clouds. Earth still blooms with life, for now, fragile and precious. Mars still remembers the water it lost. Jupiter still storms with winds older than humanity. Saturn still wears its rings, temporary crowns of ice and beauty. Uranus still rolls sideways through the dark. Neptune still races with the fastest winds in the solar system. They will continue long after we are gone. The sun will eventually expand into a red giant, consuming Mercury and Venus, possibly Earth. The outer planets will survive, orbiting a white dwarf sun for trillions of years until the last heat fades. But right now, in this brief moment of cosmic time, you are here to know them. You carry their story in your atoms, the same elements they are made of. You exist because the same processes that made planets made you. The journey is complete. 8 planets visited in thought, mysteries revealed, connections made. Tonight, when you close your eyes, you carry the cosmos with you, not as something distant and separate, but as something you are part of, something that is part of you. The planets are not just out there, they are in here, in every breath, every heartbeat, every thought. You are made of the universe, and the universe is aware of itself through you. Gravity shaped you like it, shaped the planets, pulling atoms together, creating structure from chaos. Stardust arranged itself into the pattern of a human, capable of wonder, capable of asking why, capable of understanding that the answer connects everything. The planets watch over your sleep tonight, not as distant strangers, but as ancient relatives, formed from the same cosmic dust, spinning together through darkness, part of the same story, the same family born from the collapse of a cloud 4.5 billion years ago. Sleep well under the light of distant worlds. Dream of fire and ice, of storms and silence, of rings and moons and mysteries. Wake knowing you are made of stars, forged in supernova, assembled on Earth from materials older than the sun. The planets told you their secrets, and in doing so revealed yours. You are stardust that learned to think and wonder, the universe looking back at itself with eyes made from its own atoms, asking questions that echo through the void. Good night, from Mercury to Neptune. Good night from the frost line to the Oort cloud. Good night from the dust that became planets and the dust that became you, until we journey together again among the stars, among the mysteries, among the endless beautiful dark. Sleep knowing you belong to the cosmos, and the cosmos belongs to you. The ancient watchers you asked about at the beginning are not just watching you, they are you, different arrangements of the same ancient material, all of it connected, all of it one story being told across time and space. The answer was not what science taught in school. It was something deeper, more beautiful, more personal. You are not on a planet looking up at others. You are the universe experiencing itself from one particular vantage point, made of planets, made of stars, made of everything that ever was, temporary but connected to eternity, small but containing multitudes, alone but part of everything. Rest now. The planets spin on. and you spin with them, made of them, carrying their story forward in every atom of your being until the day you return those atoms to the cosmos and they become something new, the eternal cycle of matter and energy that creates and destroys and creates again forever, without end, the dance of existence that you are part of, whether you realize it or not. Tonight, you realized it. Tomorrow you wake, knowing your place in the grand design is not separate, but integral, not small, but cosmic, not meaningless, but full of meaning that you create by being conscious, by wondering, by asking why. The 100 facts about planets were just the beginning. The real fact, the one that matters, is that you and they are made of the same ancient stardust, and that makes you family, makes you connected, makes you part of the eternal story the universe tells about itself. Sleep well, child of stars. The cosmos holds you in gravity's embrace, the same force that holds planets, that holds galaxies, that holds everything together. You are held. You are part of it all. You always were and always will be, just in different forms, the eternal transformation of matter and energy that is the heartbeat of existence itself. Good night.